Hello there and welcome to Physics with William, where curiosity gets cozy, the universe lowers its voice a little, and science takes the long way round so the mind can settle down for the night. Tonight, we are going to begin with something so ordinary that it is happening to you right now. Not in a distant galaxy, not inside a particle accelerator, not at the edge of a black hole, but right there where you are, in the quiet meeting between your body and the world around it. Perhaps your back is resting against a chair. Perhaps your head is sinking into a pillow. Perhaps your hand is curled around a warm mug, or your feet are tucked beneath a blanket, or one elbow is pressed into the mattress in that slightly awkward way you only notice once someone mentions elbows. All of these little pressures feel simple, familiar, solid. You're touching things. Things are touching you. At least that is how it seems. But here is the strange part. According to modern physics, the story is not quite so straightforward. When your hand rests on a table, the atoms in your skin are not really making contact with the atoms in the wood, in the way we usually imagine contact. There is no tiny final collision where matter meets matter, like two stones bumping together. Instead, something invisible happens before that. The electrons in your hand and the electrons in the table resist being pushed into one another. They push back through electromagnetic forces, and quantum rules quietly insist that certain particles cannot simply pile into the same states, as if the universe were a badly organised cupboard. What you feel as touch is not a direct merging of surfaces, but the result of forces, fields, and tiny restrictions acting at distances so small they are beyond ordinary imagination. The table feels firm because it refuses you, gently but decisively. Your pillow feels soft because it yields in many little ways before it refuses you. Your blanket feels warm and comforting because countless atoms and molecules are interacting with the atoms in your skin, passing energy, pressure, and signals through a hidden world of forces. So tonight, I would like you to notice something simple. What is touching you right now? Maybe it is the fabric of your sleeve. Maybe the air itself resting lightly on your face. Maybe the floor beneath your feet. Or the bed holding your whole body with such dependable patience that you have probably never thanked it. And once you've noticed that, here is the quieter question. Is it really touching you at all? Or are you being held at the thinnest possible distance by the invisible architecture of matter? That might sound like the kind of question best asked after midnight by someone staring very seriously at a sofa cushion, but it is also one of the most revealing questions in physics. Touch feels like the most direct of all senses. Sight can be fooled by mirrors. Hearing can be tricked by echoes. Smell can be suspiciously unreliable when someone claims they absolutely did not burn the toast. But touch feels honest. You press your finger against the arm of a chair and there it is. Resistance, texture, shape, the world answering back. Yet beneath that certainty is a universe that is mostly empty space, held together by interactions we cannot see. Every solid thing around you, the wall, the blanket, the cup, the book on the table, even your own hand, is made of atoms. And atoms are not miniature balls packed tightly together like oranges in a market stall. They are far stranger than that. They are tiny structures with dense centres and surrounding clouds of electrons, with most of their volume not filled by solid stuff in the everyday sense, but by space, probability, and fields. If an atom were expanded to the size of a cathedral, the nucleus would be a tiny speck somewhere inside it, and the electrons would not be little beads circling neatly like planets, but more like a spread-out possibility of where electric charge may be found. And yet, the world does not feel like a mist of emptiness. It does not behave like a ghostly arrangement of nearly nothing. You cannot simply walk through a door unless you open it, which is one of the many ways physics helps protect us from awkward social situations. You cannot place your hand through a table. You cannot step through the floor into the apartment below, which is probably for the best. Matter holds its shape. Objects press back. Bodies rest on beds. Chairs support people. Bridges hold traffic. And teacups do not dissolve through saucers. The reason is not that atoms are solid little marbles touching edge to edge. The reason is that matter is structured by forces, and those forces create the experience of solidity. Before we wander into the atomic world, let us stay for a moment with the feeling itself. Touch is intimate because it seems to happen at the boundary of you. Your skin is where your body meets the rest of reality. It is the frontier, the soft border checkpoint between self and world. When something presses against you, specialized receptors in your skin respond to pressure, vibration, stretching, temperature, and texture. These receptors send electrical signals through nerves, up the spinal cord, and into the brain, where the experience becomes something you recognize. Smooth, rough, warm, cold, heavy, light, pleasant, annoying. A cat stepping delicately onto your stomach at 4 a.m, somehow placing its entire body weight through one tiny pore. The brain then constructs the sensation of contact. It says, "Ah yes, blanket. Ah yes, mattress. Ah yes, why is there a phone charger under my shoulder?" But the nervous system is only the later part of the story. Before the nerve endings speak, before the brain interprets, before you become aware of the sensation, there is already a physical negotiation happening at the surface of matter. Your skin approaches the fabric. The atoms in your skin approach the atoms in the fabric. Their outer electrons begin to interact. Because electrons carry the same kind of electric charge, they repel one another. They do not need to touch in the little billiard ball sense to influence each other. Their electric fields extend outward, and as the atoms get extremely close, those fields push back. It is this push, transmitted through atoms and molecules and eventually through the tissue of your skin, that your nerves detect as pressure. So when you feel your blanket, you are not feeling a direct meeting of matter in the old simple sense. You are feeling resistance carried by electromagnetic interaction. You are feeling the world saying, "Not any closer, thank you very much." That phrase may sound rude, but without it there would be no ordinary world at all. If the particles in matter did not resist being compressed into the same places and states, then everything would behave very differently. Chairs would not support bodies, floors would not support chairs, books would not sit on tables, your hands would not hold shape. The world would lose the firm, reliable separations that make everyday life possible. Imagine trying to drink tea from a cup whose atoms had no meaningful objection to sharing space with the tea, the table, and eventually your lap. This would be inconvenient, at least until inconvenience became a very small problem in a universe with no solid surfaces. Now, of course, we use the word touch because it is useful. It describes what we experience. It helps us navigate life. If someone says they touched a wall, we know what they mean. There is no need to correct them by saying that their electron clouds entered a state of strong mutual electromagnetic interaction, governed by quantum mechanical restrictions. That sort of thing tends to reduce dinner invitations. In ordinary language, touch is real. It is what bodies do when they come into contact. But physics invites us to look beneath ordinary language and ask what contact actually means. At the deepest level, the idea of surfaces touching becomes less like two pieces of matter meeting and more like two regions of force becoming impossible to ignore. This is one of those moments where science does something gently unsettling. It does not tell you that your experience is false. It tells you that your experience is built from deeper processes. You really do feel the chair beneath you. You really are supported by it. The sensation is not imaginary. The chair is not a dream, unless you are already asleep, in which case the chair may have opinions of its own. But the mechanism behind that sensation is not what common sense first suggests. Solidity is not simple fullness. It is organized resistance. It is what happens when atoms, mostly empty by volume, combine through forces into structures that can bear weight, keep shape, and push back. Think of a mattress. When you lie down, it gives way. It changes shape around you. At the large scale, you can say your body presses into the mattress, and the mattress presses back. That is true enough. But inside the mattress, there is a cascade of interactions. Fibers bend, springs compress if there are springs, foam cells deform, molecules shift and resist. At every level, particles are being nudged closer together and responding through electromagnetic forces. The softness comes from how easily the structure rearranges. The support comes from how strongly it resists once rearranged. A wooden floor, by contrast, rearranges much less under your weight, so it feels hard. A pillow rearranges more, so it feels soft. Both are made from atoms that do not truly merge with you. Both are holding you through the same deep kind of refusal, expressed through different materials with different levels of politeness. Even air is touching you in its own quiet way. You may not notice it unless there is a breeze, but molecules of nitrogen, oxygen, water vapor, and other gases are constantly colliding with your skin. They are light and fast and numerous, bouncing around in all directions. Air pressure is the combined effect of these countless molecular impacts. You do not feel each one individually, just as you do not hear each separate raindrop in a distant shower as a fully independent event. Your body experiences the average, the gentle surrounding pressure of atmosphere. The air is not nothing. It is matter, moving and pressing, though softly enough that you can forget it is there. Until the wind rises, or you open a window in winter and suddenly remember that the atmosphere has opinions. When you place your hand near a hot mug, you may feel warmth even before contact. That warmth arrives partly through radiation and partly through moving air, and once you hold the mug, energy flows more directly through the material interactions between the mug and your skin. Heat is not a fluid substance passing like syrup from one object to another. It is energy moving through molecular motion and electromagnetic interaction. The molecules in the warm mug are jostling more energetically than those in your cooler hand. As the mug and your skin interact, energy spreads from the warmer material into the cooler one. Your receptors detect this as warmth. The feeling is immediate and simple, but the physics is a busy exchange of motion, energy, and forces. A cup of tea, viewed closely enough, is not just a beverage. It is a warm committee of particles enthusiastically negotiating with your fingers. This is the central theme we will slowly unfold. What you call touch is an emergent experience. That means it arises from many smaller interactions acting together. No single atom says, "I am touching the table now." No lone electron produces the whole feeling of texture, but trillions upon trillions of tiny interactions combine into the sensation of a hand on fabric, a cheek on a pillow, a foot on the floor. The everyday world is built from patterns too small to feel individually, but large enough together to become the most familiar thing there is. Touch is not one simple event, it is a chorus. And like many choruses, it can be a little untidy when you listen closely. The surfaces of objects are not as smooth as they look. Even polished glass under enough magnification has variations, bumps, and irregularities. Your skin too is textured, flexible, and alive. When two surfaces come together, they do not meet across every point evenly. Tiny high points approach first, pressure concentrates in small regions, materials deform, electromagnetic repulsion increases, atoms shift, friction appears. If you slide your finger across a wooden table, your skin catches and releases over microscopic ridges and valleys. Your nerves detect these changing patterns as texture. Smoothness is not the absence of structure. It is structure too fine, too even, or too gently arranged for your skin to register as rough. This is why touch can tell us so much. Blindfolded, you can distinguish silk from sandpaper, metal from rubber, glass from bark, warm bread from a cold spoon, which is perhaps one of the less dramatic but more emotionally important achievements of the nervous system. Your fingers are astonishing instruments. They do not just detect pressure, they read patterns of resistance. They translate microscopic surface features into useful experience. A rough surface creates irregular vibrations and changing pressure. A smooth surface offers more uniform resistance. A sticky surface forms temporary attractions with your skin. A slippery surface reduces friction, letting your hand glide. Each sensation is a different physical conversation between matter and nerve, yet underneath all of them, the same strange truth remains. The atoms are not really touching as tiny solid objects. They are interacting through fields. They are being kept apart by electric repulsion and quantum behavior. That sounds remote and technical, but it is happening right now, continuously. It is happening where your clothing rests on your shoulders. It is happening where your tongue rests against the inside of your mouth. It is happening where your lungs meet the air with every breath. It is happening between your body and the entire environment, quietly and constantly, without needing your attention. The world is not pressing into you as a collection of hard bits. It is communicating with you through forces. There is a lovely humility in this. We often think of physics as something far away, something belonging to stars, planets, particles in laboratories and complicated diagrams on chalkboards. But the mystery of matter is as close as your palm. You do not have to travel to a collider or stare through a telescope to meet the weirdness of the universe. You can press your fingers together. You can rest your hand on a blanket. You can feel the chair beneath you and know that beneath that simple sensation is a hidden world of atoms that are mostly space, electrons that refuse overlap, fields that extend without visible strings, and a brain that turns all of it into the calm certainty of touch. So let us begin there, with your own body as the laboratory. Notice the pressure of whatever is supporting you. Notice whether it feels firm or soft, broad or narrow, warm or cool. That feeling is not a mistake. It is not an illusion in the sense of being unreal. It is more like the surface of a very deep explanation. Just as the colour of the sky is real even though it comes from light scattering in the atmosphere, the solidity of the world is real even though it comes from electromagnetic and quantum behaviour rather than from tiny pieces of matter making simple contact. The experience is genuine, the explanation is stranger, and perhaps that is a comforting thought to carry into the rest of this quiet exploration. The world can be reliable without being simple. A bed can hold you even though its atoms are mostly space. A hand can rest on a table even though the deepest kind of contact never quite happens. A blanket can feel soft not because matter is touching matter in the way our imagination first pictures it, but because enormous numbers of invisible interactions combine into one gentle surface. Reality does not need to match our first guess in order to be kind. It only needs to be consistent enough that tonight, as your body settles and your thoughts loosen their grip, the electromagnetic refusal between you and the world can feel exactly like being held. If you find this kind of journey soothing, intriguing, or just a pleasant way to let the mind wander after a long day, I would be very grateful if you gave the video a like and maybe subscribed. It helps this calm little corner of science reach others who might enjoy drifting through the universe, one quiet question at a time. And if you feel like sharing, tell me where in the world you are listening from, and what is touching you right now. A pillow, a blanket, a chair, the floor, the evening air. It is a small question, but tonight it opens a very large door. Because once we start asking what touch really is, we find ourselves asking what matter is, what solidity means, and why a universe made mostly of empty space can still feel so wonderfully present. We begin with the hand and the table, but very soon we're led inward, past skin and wood and fabric, down into the crowded quiet of molecules, atoms, electrons, and the almost impossible smallness where ordinary contact disappears and something far stranger takes its place. Now that we have noticed the simple pressure of the world around us, the chair beneath you, the blanket against your skin, the floor holding its quiet place under everything, we can begin with the odd claim at the heart of tonight's little mystery. Nothing ever truly touches, not in the neat, everyday way the mind imagines. Not hand against table, not foot against floor, not raindrop against window, not even one grain of dust resting on another in the golden stripe of afternoon light. Everything seems to meet. Everything seems to press and rest and lean. But when we follow matter down into its smallest familiar structures, the idea of contact becomes less like two solid edges bumping together and more like two invisible territories refusing to overlap. It is worth beginning slowly, because common sense is very persuasive here. If you tap your finger on the table beside you, it feels obvious that your finger has touched the table. You hear the small sound, you feel the little impact, you see the fingertips stop at the surface rather than passing through. If you press harder, the skin flattens slightly and the table still holds firm. Nothing about this feels mysterious. It feels like one solid object meeting another solid object. If someone told you that your finger and the table never truly make contact, you might quite reasonably wonder if physics has been allowed to stay up too late again. But physics is not trying to deny your experience. Your finger really does stop. The table really does resist. Your nerves really do report pressure. The sound is real. The indentation in your skin is real. And the small thud may be real enough to annoy someone trying to sleep nearby. The question is not whether touch happens at the level of experience. It clearly does. The question is, what is actually happening underneath that experience? When we say two things touch, what do we mean? Do we mean that the outermost bits of one object physically merge with the outermost bits of another? Do we mean that two pieces of matter occupy the same place? Or do we mean that one object gets close enough to another that forces between them become strong enough to stop further motion? In everyday life, those possibilities all blur together. In the atomic world, they separate. Imagine two people walking toward each other in a narrow hallway. If they both stop a little before colliding because each sees the other and adjusts, did they touch? No, not in the ordinary sense. But their motion was still changed by each other's presence. Now make the hallway impossibly small, remove the people, replace them with atoms, and exchange polite visual awareness for electromagnetic interaction. Atoms do not need to crash together like tiny stones to affect one another. Their outer electrons create electric influence around them. As atoms approach, these influences begin to overlap and resist. The closer they come, the stronger the resistance becomes. Long before the dense centres of atoms could ever meet, the surrounding electron behaviour has already made closer approach extremely difficult. This is one of the first surprises. Matter is not made from little hard pellets with smooth edges. It is made from atoms, and atoms are not solid in the way pebbles seem solid. Each atom has a tiny, dense nucleus at its centre, containing most of its mass, with electrons arranged around it in a cloud-like quantum structure. Those electrons are not tiny planets circling in tidy lanes, despite the pictures many of us first met in school. Those pictures are useful at the beginning, in the same way a stick figure is useful if you are learning to draw a person. But reality is less tidy and more interesting. Electrons are described by probabilities, regions where their properties are likely to be found. The atom has no little polished outer shell where you can point and say, "There, that is the exact surface." Its boundary is more like a fading region of influence, and yet atoms make tables, walls, spoons, pillows, mountains, eyelashes and biscuits, which is a lot of responsibility for things with such uncertain edges. The reason they can do this is that atoms interact. They attract, repel, bond, vibrate and organise. Their electrons do not simply drift wherever they please. They follow quantum rules. They arrange into patterns that allow matter to form stable structures. Some atoms share electrons in chemical bonds. Some give or take electrons and hold together through electric attraction. Some form metals where electrons move more freely through a shared structure. None of this requires atoms to behave like solid beads glued together. It requires forces and rules. The world is not held together because atoms are pressed face to face like bricks. It is held together because invisible interactions create stable arrangements. Now think of your hand pressing against a wooden table. At the level of the visible world, your skin meets the surface. But the surface itself is not a perfect sheet. Wood is made from cells and fibres, from long molecules that once belonged to a living tree, from layered structures shaped by growth, water, sunlight, and time. Your skin is also layered and flexible, built from cells, proteins, oils, water, and countless microscopic textures. When the two surfaces come together, the highest tiny ridges of your skin and the highest tiny ridges of the wood approach first. Under a microscope, even a smooth table would look rugged, a landscape of small peaks and valleys. Actual contact, even in the everyday engineering sense, happens only at many small points, with spaces and gaps between them. This is why friction, wear, polish, and lubrication are such rich subjects. Surfaces are never as simple as they look from the comfortable height of a human face. But if we zoom still deeper, even those tiny points are not final contact. The atoms in your skin and the atoms in the wood approach until their electron clouds resist further compression. It is like two very soft but very stubborn atmospheres meeting. You do not feel the nuclei colliding. You feel the resistance caused by the electrons and the rules that govern them. The table pushes back not because its atoms are little rocks with hard crusts, but because the electrons in the table and the electrons in your skin cannot simply be forced into the same arrangement without a growing cost. Your hand presses, the atomic structures deform slightly, the forces increase, and that increase travels through the material and into your nerves. Your brain then translates all of it into the familiar statement, "I am touching the table." This is also why hardness and softness are not really about whether atoms touch more or less directly. They're about how the structure of a material responds when forces are applied. Press your hand into a pillow and the pillow changes shape easily. Its fibres and trapped air rearrange. Its materials bend, slide, and compress. The forces grow gradually so it feels soft. Press your hand against a wall and the arrangement of atoms is much harder to rearrange. The forces grow quickly so it feels firm. In both cases, what stops your hand is still the same broad family of physical behaviour, electromagnetic resistance shaped by quantum rules and material structure. A pillow is not more willing to let your atoms touch its atoms. It is simply more willing to reorganize itself before refusing. A useful way to picture this is not as contact, but as negotiation. Every object you press against is negotiating with you. A mattress says, "I will move a little, then hold you." A stone says, "I will hardly move at all." A rubber ball says, "I will deform, store energy, and then throw some of it back at you," which is why it bounces with a cheerfulness that can become annoying indoors. A lump of clay says, "I will deform and stay that way." A soap bubble says, "Please be gentle, I have very little patience for sharp objects." These different responses arise from how atoms and molecules are arranged, and how easily those arrangements change under pressure. But beneath the variety is the same hidden theme. Matter feels solid because it resists being pushed into matter. You might wonder then whether anything ever truly touches in a more extreme situation. What if you press hard enough? What if two objects collide violently? What about a hammer striking metal, a meteor hitting the ground, a car crashing into a wall? Surely then the atoms must touch. But even in these intense cases, the main story remains one of forces. During a collision, atoms are driven very close together, electron clouds are distorted, bonds may break, heat is produced, sound spreads, materials fracture, and enormous forces travel through the objects. Yet the nuclei of ordinary atoms still do not simply come into direct contact. They are tiny compared with the atom as a whole, and they are surrounded by electrical repulsion. To make atomic nuclei truly collide or merge, you need conditions far beyond ordinary touch, the kind found in nuclear reactions, particle accelerators, or the hearts of stars. Your finger on a table is not remotely in that category, though it may feel dramatic if the table edge finds your funny bone. So ordinary contact is really the limit of closeness allowed by the structure of matter under everyday conditions. It is the point where resistance becomes large enough to stop motion at the scale we care about. That may sound less satisfying than saying things touch, but it is actually more wonderful. It means every object around you is surrounded by an invisible zone of interaction. The boundary of a thing is not merely where its visible surface ends. It is where its forces become important to another thing. The world is full of these quiet boundaries, and your body is constantly moving among them. This brings us to another subtle point. If atoms are mostly empty space, why can we not pass through objects? It is one of those questions that sounds almost childish in the best possible way, because children often ask the questions adults have learned to step around. If matter is mostly empty, why does the wall stop you? The answer is that empty space inside atoms is not empty in the sense of being available for other atoms to casually occupy. It is not like an empty parking space waiting for a tiny car. It is a region governed by fields, energy, and quantum structure. The electrons of atoms are not little decorations around a hollow center. They define how atoms interact. When another atom approaches, it encounters those interactions, not a vacant room with a welcome mat. A cathedral may be mostly air inside, but that does not mean you can place another cathedral in the same space without moving walls, floors, pillars, people, candles, and possibly a very startled organist. In a similar way, the open volume of an atom is structured. It is filled not with solid stuff, but with rules and possibilities that still have physical consequences. The fact that atoms are mostly empty does not make matter flimsy. It makes matter subtle. Solidity does not require every point to be packed with substance. It requires stable resistance to compression and overlap. A trampoline is mostly empty space too if you look at it one way. What matters is not whether every bit of its area is filled, but whether its structure can respond when you land on it. The deeper we go, the more the old picture of touching becomes a habit of scale. At human size, it is sensible to talk about surfaces touching. Engineers, doctors, cooks, sculptors, and tired people reaching for blankets all use that language well. At the scale of atoms, surfaces are not sharp and contact is not a simple bump. What we call touching is the large-scale result of tiny interactions that never look like our common-sense picture. This happens often in science. Temperature feels like warmth or cold, but underneath it is the motion and energy of particles. Sound feels like a continuous tone, but underneath it is pressure waves moving through matter. Colour feels like a property of objects, but underneath it is light interacting with surfaces and eyes. Touch feels like direct contact, but underneath it is electromagnetic and quantum behaviour being interpreted by a nervous system. There is a small comfort in realising how much of the familiar world is built this way. Reality is layered. Each layer has its own language. You do not need to think about electron repulsion to enjoy the softness of a blanket, just as you do not need to think about photosynthesis to enjoy sitting under a tree. But when you do think about it, the ordinary becomes richer. The blanket is still soft, the tree is still shady, the table is still sturdy. But now each one carries a hidden depth. The world has not become less real, it has become more interesting. Let us linger with the example of pressing your palms together. It is a simple thing. You can do it quietly without much effort. At first you feel warmth and skin. Press a little more and the tissues compress. Blood shifts slightly. The skin deforms. Nerves respond. You may feel the ridges of your fingerprints. But your left palm does not merge with your right palm. The atoms in one hand are not sliding into the atoms of the other. The outer electrons of the molecules in your skin are resisting closer approach. The cells in your skin are held together by molecular structures, and those structures resist deformation. The pressure you feel is your own body meeting itself through invisible forces. You are, in a very real sense, preventing yourself from passing through yourself, which is just as well. Biology is complicated enough without that. Even a kiss, one of the most intimate forms of touch, is still governed by this same physics. Soft tissues deform. Warmth transfers. Nerve endings awaken. The brain adds emotion, memory, expectation and meaning. But beneath all that, the atoms remain atoms, separated by the rules of matter. The closeness is real at the human level. The feeling is real. The tenderness is real. Yet even there, where touch feels most direct, the deepest physics says there is still a minute refusal, an invisible separation that makes the sensation possible. It is oddly beautiful. What keeps things apart is also what allows them to feel close. The same is true when you hold a pet, shake a hand, hug someone, or rest your forehead against a cool window. Contact is not made less meaningful because matter does not merge. In fact, the separation is what preserves identity. Your hand remains your hand, the window remains the window, the cat remains the cat, and will continue to believe it owns the furniture. If atoms truly passed into one another without structure or resistance, the world would lose the boundaries that make relationships possible. Touch depends on difference. It depends on one thing being near another thing without becoming the same thing. Physics does not erase closeness. It explains the conditions that allow closeness to exist. There is also a useful distinction between touching and interacting. In everyday language, touch is a form of interaction that requires closeness. In physics, interaction is the broader idea. Objects can influence each other without visible contact. A magnet pulls on another magnet through a magnetic field. Earth pulls on the moon through gravity. A charged balloon can tug at tiny bits of paper. You do not see little hands reaching out, but the influence is there. Touch belongs to this family. It is not magic contact. It is one of the ways interactions become strong enough, close enough, and organized enough for bodies to notice. The difference is that touch feels immediate because the forces are transmitted through the surfaces and tissues involved. The fields do the tiny work, and the nervous system turns at work into sensation. When you sit in a chair, you're participating in an enormous stack of such interactions. Your body presses on the chair presses on the floor presses on the beams or concrete beneath it, the building presses on the ground presses back. At every level, matter resists matter, not through tiny final collisions, but through the combined behavior of atoms and forces. The support feels passive, as if the chair is simply there. But at the microscopic level, it is active in the sense that countless particles are responding to compression and maintaining structure. You're not falling through the chair because the chair is continuously refusing your fall, quietly, faithfully, without asking for applause. This is why the phrase "nothing ever truly touches" should not be heard as a bleak statement. It is not saying we are isolated ghosts drifting through an untouchable world. It is saying that touch is more subtle than we first imagined. We are not separated from the world by emptiness alone. We are connected to it by interaction. Every pressure on your skin is evidence of a relationship between your body and something else. The invisible forces that prevent atoms from overlapping are the same forces that let you hold a book, feel a hand, walk on a path, lie down in bed, and know the shape of a cup in the dark. The separation is not absence, it is structure. At this point, the mind may want a final boundary, a place where it can say, yes, but surely here is the surface, here is where one thing ends and another begins. But atomic reality resists that neatness. The surface of an object is not an infinitely thin border, it is a region. Electrons extend outward in probabilistic ways. Molecules vibrate. Atoms at a surface behave differently from atoms deeper inside. Air molecules may cling briefly to it. Moisture may form a thin layer. Dust may settle. Oils from your skin may remain after you touch it. A surface is more like a busy neighborhood than a clean geometric line. This is one reason real materials have such complex behavior. Adhesion, friction, wetting, polishing, scratching, and sticking all depend on what happens in this surface region, where the identities of objects come near but do not simply merge. Consider tape sticking to paper. At first glance, that seems like a counterexample. Surely if tape sticks, it must touch very directly. But adhesion is another interaction story. The sticky surface flows into tiny irregularities. Molecules get close enough for attractive forces to matter. Weak electromagnetic attractions form between the adhesive and the paper. The result is a bond strong enough to hold them together until you peel it away, perhaps removing more paper than intended and making a sound that feels unreasonably loud in a quiet room. Even sticking is not true matter merging. It is closeness plus attraction plus material softness plus surface structure. It is contact as cooperation, not collision. Or think of water wetting your skin. A drop of water spreads, clings, cools, and leaves a sensation very different from dry fabric or metal. Water molecules are polar, meaning their electric charge is distributed unevenly, and that lets them interact strongly with many surfaces. Your skin has oils, salts, proteins, and textures that shape how water behaves on it. The feeling of wetness is actually a blend of pressure, temperature change, and the way water alters friction on the skin. Interestingly, humans do not have a single simple wetness sensor, like a little internal rain alarm. The brain infers wetness from several signals at once. Even here, where water seems to touch us so plainly, the experience is a construction built from interactions. The more examples we examine, the clearer the pattern becomes. Touch is not a single thing. It is a family of experiences produced by forces at boundaries. Hardness, softness, stickiness, slipperiness, wetness, warmth, vibration, texture, pressure, and pain are all different reports from the frontier between body and world. Your skin is the instrument, your nerves are the cables, your brain is the interpreter, and atomic forces provide the hidden music. Though perhaps music is too graceful a word for stepping barefoot on a small toy in the dark. That particular performance is more of a percussion event. Still, even pain follows the same broad chain. Step on something sharp, and the pressure becomes concentrated in a tiny area. The material of your skin deforms strongly, possibly enough to damage cells. Nerve endings designed to detect harmful pressure send urgent signals. The brain responds quickly, and suddenly the elegant mystery of atomic interaction is replaced by the very practical mystery of who left that there. The sharp object did not need its atoms to truly touch your atoms in some final metaphysical sense. It needed only to focus force strongly enough to harm tissue. The body cares less about philosophical contact and more about staying intact, which is probably wise. As we move through this idea, it is important not to overstate it in the wrong direction. When physicists or science communicators say nothing truly touches, they're usually speaking from the atomic perspective, where ordinary contact is not a collision of hard surfaces. But in everyday and even many scientific contexts, contact is still a valid and useful concept. A tire contacts the road, a foot contacts the floor. A doctor checks contact between a medical sensor and the skin. These statements are not wrong. They operate at the scale where contact means force transmission through adjacent materials. The deeper explanation does not abolish the practical one, it supports it from below. That is a recurring theme in science. Older or simpler descriptions do not always vanish when deeper ones arrive. They become part of a layered understanding. You can still say the sun rises, even though Earth is rotating. You can still say a room is warm, even though warmth comes from particle motion and radiation. You can still say your hand touches the table, even though at the atomic level the sensation comes from repulsion, structure, and quantum rules. Language belongs to the scale of life. Physics lets us peek beneath that scale, but it does not require us to become impossible people at breakfast. Nobody wants to hear, "Please pass me the object whose electron clouds are electromagnetically resisting the electron clouds of the table." Just say mug, it is kinder. And yet, once you know this, the ordinary gesture changes. Resting your hand on a table becomes a meeting of invisible fields. Sitting on a chair becomes an act of atomic balance. Walking across a room becomes a sequence of controlled repulsions between your feet and the floor, each step a brief agreement that the ground will push back just enough for you to move forward. The world feels less like a collection of solid blocks and more like a stable dance of interactions. Everything that seems still is still only at our scale. Inside it, atoms vibrate, electrons occupy quantum states, molecules flex, and forces maintain the shapes we trust. There is something calming about that, especially at night. The bed beneath you is not a dead slab of stuff. It is a vast organized system of matter responding to you. Your body is not simply lying on it. Your body and the bed are engaged in a quiet physical exchange. Pressure spreads, materials deform, heat moves, air shifts, nerves report. The brain softens the information into comfort or discomfort, depending perhaps on whether the pillow has somehow migrated into the least helpful possible position. Even stillness is full of activity, but the activity is so balanced, so steady, that it becomes rest. So when we say nothing ever truly touches, we are not taking touch away. We are giving it a deeper biography. We are saying that the feeling of contact has ancestors in electromagnetism, quantum rules, atomic structure, material science, biology, and perception. We are saying that the solid world is not solid because it is packed completely full, but because its parts know how to resist, attract, bond, and organize. We are saying that the boundary between you and everything else is not a harsh line, but a region of interaction where the universe becomes personal. And perhaps that is why touch feels so immediate. It is physics arriving at the skin and becoming experience. For now, let the idea settle gently. The blanket against you is not simply lying there. The chair beneath you is not merely a shape. The air on your face is not quite nothing. All of it is interacting with you, close enough to matter, close enough to be felt, but never in the simple way of tiny solid things finally meeting. The world is held at a distance so small it vanishes from daily awareness, yet that distance is what allows pressure, texture, warmth, support, and comfort to exist. And as we follow that distance inward, the next step is to look more closely at the atoms themselves, those strange little structures that make up everything familiar while being, in their own quiet way, almost nothing like the solid world they create. If we want to understand why the world feels solid, the next place to look is not the table, the floor, or the chair as they appear to us, but the atoms beneath that appearance. These atoms are the quiet building blocks of everything familiar. They make the wood in a desk, the cotton in a pillowcase, the glass in a window, the minerals in a stone, the water in your skin, and the air moving softly in and out of your lungs. They are so small that ordinary imagination has trouble holding them properly. We can say an atom is tiny, but tiny is a word that was made for crumbs, seeds, dust, and perhaps that last little piece of biscuit left in the tin. Atoms are far beyond that. They're not just small in the way a grain of sand is small. They belong to a scale where size stops feeling like a normal idea and becomes more like a reminder that human senses were designed for fruit, weather, faces, and furniture, not the deep architecture of matter. For a long time, people imagined matter as something continuous. A stone seemed to be stone all the way through. Water seemed to be water all the way down. Wood, bone, skin, metal, bread, salt. Everything seemed to be made of its own kind of stuff. If you cut a piece of cheese in half, there is cheese inside. Cut it again. Still cheese. Keep going in thought, slicing smaller and smaller. And it is tempting to imagine that you would simply find smaller pieces of cheese forever, which is an idea both scientifically incorrect and emotionally quite appealing. But nature has a different arrangement. Matter is not continuous in that simple sense. It is made of discrete units, atoms and molecules, arranged in ways that give substances their properties. The cheese is not cheese all the way down. At some point it is proteins, fats, water, minerals, molecules, atoms, nuclei, electrons, and a set of interactions that are doing a great deal of work before breakfast. The word atom originally suggested something indivisible, something that could not be cut. That was a reasonable guess from ancient thinkers who imagined that if matter was divided enough, eventually one must arrive at a smallest piece. Modern physics has shown that atoms are not indivisible in the strict sense. They have parts. At the centre is a nucleus, incredibly small compared with the whole atom, yet containing nearly all of its mass. Around that nucleus is the electron cloud, a region shaped by quantum rules, where electrons are not little planets on neat tracks, but are described by patterns of likelihood. The atom is not a miniature solar system, even though that image has been drawn so many times that it now lives in the public imagination like a very persistent houseguest. It is better to think of an atom as a compact centre surrounded by a spread-out region of electric influence and quantum possibility. This is where the strange phrase "mostly empty space" enters the room, sits down, and makes everything feel slightly less ordinary. Atoms are mostly empty by volume. If the nucleus were enlarged to the size of a small pebble, the outer region of the atom would extend across a space far larger than the pebble itself, perhaps across a room, a hall, or even a building depending on the comparison being used. The exact analogy changes from one explanation to another, but the lesson is the same. The nucleus is tiny compared with the overall size of the atom. The rest is not filled with solid material in the everyday sense. It is a region where electrons are described by quantum states, where electric forces matter, where probabilities replace neat little paths, and where the ordinary idea of a filled object begins to dissolve. This can feel deeply unsettling at first. If atoms are mostly empty space and everything is made of atoms, then why does anything feel solid? Why does your hand not sink into the arm of the chair? Why does a book sit on a shelf instead of slowly drifting through it like a shy ghost? Why does a wall keep being a wall instead of a polite suggestion? These are excellent questions, the sort of questions that make physics both beautiful and slightly inconvenient. The answer is that empty space inside atoms is not empty in the same way a glass jar is empty before you put buttons in it. It is not available space in which other atoms can simply settle down. It is structured by forces and quantum rules. The electron cloud is not a decorative mist around a solid centre. It is the part of the atom most responsible for how atoms meet, bond, repel, and form the stable world around us. When one atom approaches another, the outer electrons are the first to matter. They carry electric charge, and they respond to the presence of other charged particles. Under some circumstances, atoms attract and form bonds. Under other circumstances, they resist being pushed closer. Both attraction and repulsion are essential. Without attraction, atoms would not form molecules, crystals, fibers, liquids, or living cells. Without repulsion and quantum restrictions, matter would not hold its shape or occupy space in the way it does. The solidity you feel is not the result of atoms being packed completely full. It is the result of atoms being held in arrangements that resist compression. Their emptiness is not weakness. It is a stage on which powerful rules are operating. Think of a crowd in a quiet room. If the room is not full of bodies from wall to wall, you might say there is empty space between people. But that does not mean anyone can walk through without being noticed. The people can move, adjust, make room, resist, or block the way. The space between them has social structure, if you like. There are patterns and boundaries. Atoms are not people, of course, and electrons are not politely avoiding eye contact near the snack table, but the analogy helps loosen the idea that empty means irrelevant. The space in and around atoms is not a blank nothing. It is part of the structure. It is where interactions happen. A solid object, then, is not solid because it has no empty space. It is solid because its atoms are arranged in a stable pattern and strongly resist being displaced from that pattern. In a crystal of salt, atoms are arranged in a repeating structure, held together by electric attraction between ions. In a diamond, carbon atoms form a rigid network of strong bonds, which is why diamond is hard and why it has such a confident reputation. In a piece of metal, atoms sit in a lattice, while some electrons move more freely through the structure, giving metals their shine, conductivity, and that particular cold feeling when you touch a metal spoon before it has had the decency to warm up. In wood, long organic molecules and cellular structures create a material that is strong in some directions, weaker in others, textured, fibrous, and shaped by the life of a tree. Each material feels different because its atoms and molecules are arranged differently, and because those arrangements respond differently when pressed, bent, heated, scratched, or stretched. This is why a stone and a sponge can both be made of atoms and yet feel completely different in the hand. The stone has atoms locked into mineral structures that resist deformation. The sponge has a network of flexible material with many gaps that can collapse and expand. Press a stone and very little changes. Press a sponge and the structure rearranges easily. The difference is not that stone atoms are more truly touching than sponge atoms. The difference is in the organization. Matter is architecture at a scale too small to see. Solidity is not merely substance, it is arrangement. The same principle applies to your own body. Your skin feels soft because it is made of a living tissue, layers of cells, proteins, fats, water, and flexible structures that can deform. Bone feels hard because its material is mineralized and organized to resist compression and bending. Hair is flexible because of its protein structure. Nails are harder because of densely packed keratin. The body is not one kind of matter, but a whole library of materials, each with its own atomic and molecular arrangement. Your sense of touch reads these differences from the outside, but they begin deep inside the organization of atoms. A fingertip can tell silk from wool, glass from paper, metal from plastic, not because it sees atoms, but because it detects how surfaces resist, drag, vibrate, conduct heat, and shift under pressure. Now let us return to the idea of empty space, because it has a habit of being misunderstood. When people hear that atoms are mostly empty, they sometimes imagine that matter should be easy to pass through, if only one could line things up correctly. After all, if most of a wall is empty space, perhaps there should be a chance of walking through it with the right attitude and a little determination. Unfortunately, walls are not impressed by attitude. The emptiness of atoms does not mean the wall is full of open tunnels at the human scale. The atoms in the wall are arranged with electron clouds, chemical bonds, and electric fields. Your body is made of atoms arranged in another stable structure. As you approach the wall, the outer electrons of your atoms and the outer electrons of the wall's atoms interact strongly. Those interactions prevent the two structures from occupying the same region. Under ordinary conditions, you're not blocked by little solid spheres filling every point. You are blocked by fields and rules that are extremely good at their jobs. This is one reason matter can be both mostly empty and very strong. A bridge, for example, is not strong because every microscopic bit of its volume is filled with unbroken solid essence. It is strong because its materials are arranged to distribute forces. Steel, concrete, stone, and wood all manage stress through structure. At the atomic level, bonds stretch and resist. At the larger level, beams carry loads, arches redirect pressure, and supports transfer weight into the ground. Solidity grows upward from microscopic interactions into engineering. The bridge holds a truck for the same broad reason a chair holds you, because matter resists being compressed and displaced. The details differ enormously, but the principle begins in atomic structure. If you could shrink down and wander through a solid object, which is not recommended as a practical travel plan, you would not find a smooth, continuous interior. You would find regions of charge, vibrating atoms, molecular arrangements, and patterns of space. In a crystal, there would be order repeating again and again. In a polymer, long chains would twist and tangle. In a biological tissue, there would be membranes, water, proteins, fibers, and moving molecules. Matter is busy. Even a still object is not truly still. Atoms vibrate, molecules rotate and flex. Electrons occupy changing quantum states. Heat is the sign of this motion. At absolute stillness, a place ordinary matter never quite reaches in normal life. Even then, quantum rules do not allow the simple frozen picture our minds might expect. The world beneath solidity is alive with activity, though not alive in the biological sense. It is dynamic, restless, structured movement. This helps explain why temperature changes how things feel. A metal railing on a cold morning can feel much colder than a wooden fence at the same temperature, because metal conducts heat away from your skin more efficiently. Your skin does not directly measure temperature like a perfect thermometer. It responds to the flow of energy. Metal pulls heat from your fingers quickly, so it feels cold. Wood does so more slowly, so it feels less cold. The atoms in both materials are interacting with the atoms in your skin, but their internal structures transfer energy differently. Again, the sensation is a large-scale interpretation of atomic behavior. Your body says cold metal, and physics says fast energy transfer through a material with mobile electrons and efficient vibrations. Your body wisely chooses the shorter phrase. The feeling of solidity is also tied to time. Press briefly on a material, and it may seem firm. Press slowly, and it may flow. Glass, for instance, is rigid at ordinary human timescales, despite common myths about old windows flowing noticeably over centuries. Honey, on the other hand, resists quick motion but slowly pours. Some materials behave like solids under sudden stress, and fluids under slower conditions. A mixture of starch and water can feel firm when struck and liquid when handled gently, which is both a science demonstration and a kitchen cleanup warning. These examples show that solidity is not a single absolute property. It depends on structure, force, temperature and time scale. Atoms and molecules are always involved, but how their arrangements respond can vary dramatically. Even the air around you has solidity of a kind, though it is so gentle and fluid that we usually call it pressure rather than solidity. Air molecules are separated by much larger distances than atoms in solids or liquids, but they still collide, move and exert force. You can wave your hand through air because the molecules move aside easily. Try waving your hand through water, and the resistance grows because water molecules are closer together and interact more strongly. Try waving your hand through a wall, and the wall will decline the invitation. Solids, liquids, and gases are not different, because one is made of real matter, and the others are less real. They are different states of matter, shaped by how particles are arranged and how they move. The world that feels solid is one possible behavior of atoms among several, and it happens when their interactions create stable structure. At the level of daily experience, the emptiness inside atoms is hidden from us. Our senses average over enormous numbers of particles. When you rest your hand on a tabletop, you're not feeling individual atoms. You're feeling the collective response of an unimaginable number of them. Your skin compresses over a region containing countless molecules. The table's surface responds across countless atoms. Signals from many receptors combine into one clear sensation. This averaging is why the world feels smooth and continuous. Your senses do not report the grain of reality at the atomic scale. They report what matters for survival and action. Is the surface stable? Is it hot? Is it sharp? Is it moving? Is it safe to lean on? The brain is not trying to produce a physics lecture every time you touch a spoon, which is fortunate, because breakfast would take ages. Still, there are moments when the hidden granularity of matter leaks into experience. A rough surface feels rough because microscopic irregularities create changing pressure and vibration. Powder feels grainy because it is made of small particles that move against one another. Sand slips and resists at the same time because grains rearrange under force. A polished surface feels smooth because its irregularities are small compared with the sensitivity of your skin, and because friction is more uniform. These sensations are not direct views of atoms, but they are reminders that surfaces are made, not simply given. Every texture is an arrangement of matter at scales below sight. The same is true of sound when you tap an object. A wooden table produces one kind of knock, a glass another, a metal bowl another, and a pillow mostly produces a soft disappointment. The sound depends on how the material vibrates after being struck. Those vibrations travel through atoms and molecules, through bonds and structures, then into the air, then into your ear. The hardness you feel and the sound you hear are related. Both come from how matter responds to force. Solid objects are not silent blocks of stillness. They can ring, thud, crack, creak, hum, or squeak, depending on the way their atoms and structures pass motion along. A squeaky chair is, in its own humble way, an unwanted lecture in material physics. The idea that atoms are mostly empty also changes how we think about weight. When you hold a book, it feels substantial. Its mass is mostly in the nuclei of its atoms, packed into tiny centres. But the book's size, shape, and surface come mainly from electron behaviour and molecular structure. The heavy part and the spacious part are not the same thing. Most of the mass sits in the nuclei, while most of the volume is defined by electrons and their quantum states. So when you say the book is solid, you are describing the way its electron structures resist your hand. When you say it is heavy, you're describing how its mass responds to gravity. These two everyday impressions, solidity and weight, feel unified in the object, but physics shows they come from different aspects of matter. This distinction is useful because it reminds us that our senses bundle reality together. An object feels like one thing. A mug is warm, smooth, heavy, and hard. But each property has its own explanation. Warmth comes from energy transfer. Smoothness comes from surface structure. Weight comes from mass under gravity. Hardness comes from resistance to deformation. Solidity comes from electromagnetic and quantum behaviour, organised through atoms and molecules. The mug is not less real because its properties have different roots. It is more fully understood. It is a small, everyday object made from layered causes. Also, it may contain tea, which improves almost any explanation. As we keep following the idea inward, we encounter a truth that is easy to say and hard to feel. Matter is not what it seems, yet it reliably becomes what it seems. Atoms are mostly empty, yet tables hold. Electrons are not little solid beads, yet surfaces press back. Nuclei are tiny, yet mass is real. Quantum rules are strange, yet chairs remain dependable. The familiar world is an emergent world. That means its ordinary properties arise from the combined behaviour of many smaller things. No individual atom is a chair. No single molecule is a blanket. No lone electron is soft, hard, wet, or rough in the way we experience those qualities. But gather enough atoms in the right arrangement, and suddenly there is oak, cotton, glass, skin, water, stone, bread, and the entire practical universe of touch. Emergence can sound mysterious, but it is common. A single water molecule is not wet in the usual sense. Wetness appears when many water molecules interact with each other and with surfaces. A single air molecule is not wind. Wind appears when many molecules move together in a pattern. A single neuron is not a thought. Thoughts arise from vast networks of activity in the brain. In the same way, solidity is not a property of little hard atoms. It emerges from how atoms interact in large numbers. The world feels solid because an enormous hidden population of particles is behaving collectively in stable ways. This is why the phrase empty space should not make the world feel less present. Emptiness is part of the design. Without the spatial structure of atoms, without electron clouds extending outward, without rules preventing collapse and overlap, matter would not have chemistry, shape, or touch as we know it. The space inside atoms allows complexity. It allows electrons to form bonds, atoms to arrange into molecules, molecules to build cells, cells to form tissues, and tissues to create hands that can rest on tables and wonder why tables feel solid. The emptiness is not a flaw. It is room for interaction. There is a quiet elegance in realizing that your sense of the world depends on scale. At your scale, the chair is solid. At the atomic scale, it is structured emptiness governed by forces. At the nuclear scale, it is tiny, dense centres separated by distances enormous compared with their own size. At the quantum scale, it is probabilities and allowed states. None of these views cancels the others. They are different layers of the same reality. The chair does not stop being a chair because it is made of atoms, just as a song does not stop being a song because it is made of vibrations in air. The deeper description explains how the higher one becomes possible. So as you sit or lie wherever you are, supported by matter that is mostly empty by volume, there is no need to feel that support is fragile. Quite the opposite. It is astonishingly dependable. The atoms beneath you are not tiny bricks packed without gaps. They are organised systems of forces that resist, bend, vibrate, and settle into balance. Your body rests on that balance. Your skin reads it as pressure. Your brain accepts it as the ordinary comfort of being held by a surface. But beneath that comfort is one of the great tricks of the universe, that emptiness can build solidity when it is shaped by the right rules. And from here, the next question comes naturally. If atoms are mostly space, and if their surfaces are not hard edges in the everyday sense, then what actually keeps your hand from passing through the table? What is doing the pushing before anything truly meets? To answer that, we need to look more closely at the invisible cushion between things, the electromagnetic interaction that turns nearness into resistance and makes the almost empty world feel firm beneath your fingertips. To answer why your hand does not pass through a table, we have to spend some quiet time with one of the most familiar and powerful forces in the universe, though familiar is a slightly funny word here, because most of us do not spend breakfast thinking about it. Electromagnetism is everywhere in ordinary life. It is in light, electricity, magnetism, chemistry, touch, friction, warmth, nerve signals, and the reason your socks cling together from the dryer, as if they have formed a small emotional support group. It is also the main reason the world pushes back when you press against it. Gravity may get the grand reputation because it keeps planets in orbit and makes dropped biscuits land on the floor with tragic consistency. But when it comes to the feeling of contact, electromagnetism is doing most of the immediate work. The word electromagnetic can sound like it belongs in a laboratory full of coils, sparks, and serious people wearing protective glasses. But it is also happening right now, quietly, in the place where your body meets whatever is supporting it. Your skin is made of atoms. The chair, bed, blanket, or floor near you is made of atoms. Atoms contain electrically charged particles. Protons in the nucleus carry positive charge. Electrons around the atom carry negative charge. Opposite charges attract, like charges repel. This simple rule, which sounds almost too plain for something so important, shapes much of the physical world. It helps hold atoms together. It allows molecules to form. It governs how materials bend, stretch, resist, stick, slide, conduct electricity, reflect light, and press back against your hand. When your finger approaches a table, the outer parts of the atoms in your finger approach the outer parts of the atoms in the table. Those outer parts are mostly electrons. Electrons do not behave like little hardballs, but they do carry negative electric charge, and negative charge repels negative charge. So as the electron clouds in your skin come very close to the electron clouds in the table, they resist being pushed into one another. That resistance grows very quickly at extremely small distances. You never feel a tiny click where solid edges meet. Instead, you feel the effect of this growing resistance as pressure. The table seems to have a surface because there is a region where pushing farther becomes difficult. The surface is not a sharp wall in the atomic sense. It is more like a boundary made of force. This is the electromagnetic cushion. It is not a cushion you can see, and it is not soft in the way a pillow is soft. It is a zone of interaction between charged particles. It holds things apart. It allows objects to press on each other without merging. It is the reason your finger stops at the tabletop and does not continue downward into the wood. is not exactly a layer sitting between you and the table like cling film. It is more accurate to say that the fields and charges of the atoms begin to interact strongly when they are brought close together. But cushion is a useful image, because it reminds us that the stopping happens before the old picture of direct matter to matter contact. You're held away from the table by forces acting across a very tiny distance. The idea of a force acting across space may seem strange, but you already know examples of it. Hold two magnets near each other, and you can feel them pull together or push apart before they touch. Bring a charged balloon near your hair, and your hair may lift toward it, which is one of the more undignified demonstrations of physics. Rub your feet on a carpet and touch a metal doorknob, and a small spark may jump before your finger fully settles on the metal. In each case, something happens through a field. A field is a way of describing influence spread through space. It tells a charged particle what force it would feel at a particular place. We do not need to see the field for it to be real. We can see what it does. At the atomic scale, electric fields are not a side detail, they are essential. The electrons in atoms respond to the positive nuclei of their own atoms, and to the electrons and nuclei of nearby atoms. When atoms are far apart, their interactions may be weak. When they come close, the details matter more. Sometimes the arrangement leads to attraction. This is how atoms can bond and form molecules. Sometimes the arrangement leads to strong repulsion. This is what stops matter from collapsing into matter under normal conditions, and often there is a balance. Atoms settle at certain distances from one another because attraction and repulsion find a stable arrangement. Push them closer and repulsion increases. Pull them apart and attraction may draw them back, depending on the material. This balance is what gives substances their structure. A material is, in a very practical sense, a pattern of electromagnetic relationships. In a wooden table, atoms are connected into molecules and fibers by chemical bonds. Those bonds are electromagnetic in origin. The electrons and nuclei arrange themselves in stable ways. The table holds its shape because disturbing those arrangements takes energy. When your hand presses down, you're trying, very slightly, to deform the surface. The atoms in the table shift by tiny amounts. Their electron clouds distort. Bonds stretch and resist. That resistance spreads through the material. The table pushes back. Your skin also deforms, and the tissues in your finger push back too. The final sensation is not one object simply hitting another. It is a mutual adjustment of two enormous atomic systems, each resisting the other through electromagnetic interaction. This is why pressure can be transmitted through solid objects. If you press one end of a wooden ruler, atoms at that end shift slightly. They push on neighbouring atoms through their bonds and electric interactions. Those atoms push on the next atoms and the effect travels through the ruler. The atoms do not need to move very far, they only need to disturb each other. A solid object can carry force because its atoms are connected in a stable network. A liquid carries force differently because its molecules can slide around more easily. A gas carries force differently again because its molecules are far apart and move freely between collisions, but in all cases the interactions between charged particles are central to how matter responds. The electromagnetic cushion also explains why different surfaces feel different. A polished glass surface feels smooth because its surface irregularities are small and arranged in a way that lets your skin glide more evenly. A piece of sandpaper feels rough because tiny hard grains create rapidly changing pressure points. A rubber surface feels grippy because its molecules can deform and interact with your skin in ways that increase friction. A metal spoon feels hard and often cold because its atomic structure resists deformation and conducts heat away from your skin efficiently. These differences come from material structure, and material structure is built from electromagnetic relationships among atoms. What your fingers call texture, physics calls a complicated pattern of forces, motion, surface shape and energy transfer. Your fingers are more concise, which is helpful when you are choosing a sweater. Friction is a good place to see the cushion at work because friction feels so ordinary. Slide your hand across a table and you feel resistance. Slide it across ice and there is much less. Slide it across a sticky surface and suddenly the universe becomes unreasonably committed to slowing you down. At a small scale, friction comes from many effects working together. Tiny bumps on surfaces catch and release. Molecules attract each other briefly. Materials deform. Energy is converted into heat. The electromagnetic interactions between atoms and molecules control much of this behavior. Surfaces are not perfectly smooth sheets meeting like ideal geometry. They are uneven landscapes brought close enough for their atoms and molecules to interact. When you slide one surface over another, you're dragging one atomic landscape across another, and the electromagnetic cushion is constantly changing shape, resisting, sticking, releasing, and warming the material slightly as motion becomes heat. This is why rubbing your hands together makes them warm. Your palms do not warm because skin is simply scraping against skin in the simple sense of two solid slabs grinding. At the microscopic level, tissues deform, ridges in the skin move over one another, molecules interact, and mechanical energy becomes increased molecular motion. Your body interprets that increased energy as warmth. The same electromagnetic interactions that stop your hands from passing through each other also help turn motion into heat when surfaces slide. A small, everyday gesture becomes a tiny lesson in energy transfer. It is also useful in winter, which is physics being practical for once. Static electricity is a more noticeable version of electromagnetic behavior. When you rub certain materials together, electrons can be transferred from one surface to another. One object ends up with more negative charge, the other with less. Then the objects can attract or repel each other. Your hair may stand up, a balloon may stick to a wall, a spark may jump from your fingers to a doorknob. These effects are not separate from touch. They are reminders that surfaces are electrically active. Even when there is no dramatic spark, charged particles are still responsible for how materials meet. The quiet push between your hand and a table belongs to the same family as the little zap from a sweater, just calmer and less likely to make you blame the furniture. It may help to think about scale again. At our scale, the table surface seems still. At the atomic scale, electrons and nuclei are constantly involved in motion and interaction. The electron clouds are not hard shells, but they have structure. When another atom comes close, that structure changes. It may be distorted, it may shift, it may repel more strongly. These changes happen over distances far too small for human senses to separate, so your brain receives the final result as a clean sensation. Firmness, smoothness, pressure. But underneath, the boundary is active, responsive, and made from fields. Light itself is electromagnetic, which means the same broad force family responsible for touch is also responsible for sight. When you see a table, light interacts with the electrons in its surface. Some wavelengths are absorbed, some are reflected, and the reflected light reaches your eyes. When you touch that table, the electrons in your skin interact with the electrons in the table and produce resistance. So the table you see and the table you feel are both being revealed by electromagnetism in different ways. Sight uses electromagnetic waves traveling through space. Touch uses electromagnetic forces acting at close range between atoms. In both cases, the table is not simply presenting itself directly to you. It is interacting with you, and your nervous system is interpreting the result. Reality is very sociable in that sense. It is always arriving through interaction. This also means that the surfaces of things are not passive. A surface is a place where atoms have fewer neighbours than atoms inside the material. That makes the surface chemically and physically interesting. It can attract molecules from the air. It can hold a thin layer of moisture. It can oxidize as iron does when it rusts. It can gather dust. It can be polished, scratched, coated, painted, or made sticky. Every surface has a kind of history written in its outer atoms. When you touch an old wooden banister, your skin is not only meeting wood in a general way, It is meeting oils from hands, worn fibres, dust, polish, moisture, and tiny changes accumulated through years of contact. The electromagnetic cushion carries not just resistance, but the details of the surface. This is why old objects can feel different from new ones, even when they are made of similar material. Time changes surfaces, and touch reads those changes. One of the interesting things about the electromagnetic force is that it can both hold matter together and keep matter apart. At first, that sounds contradictory, like a person who invites you to dinner and then stands in the doorway. But it depends on arrangement and distance. Electrons are attracted to positive nuclei, and this attraction helps form atoms. Atoms can share or exchange electrons in ways that create chemical bonds. Molecules can attract one another through weaker electric effects. These attractions make matter cohesive. They let water form droplets, glue stick paper, and solids hold together. But when atoms are pushed too close, the repulsion between electrons and the deeper quantum restrictions become dominant. Matter then strongly resists further compression, so the same general force family is responsible for both connection and separation. It lets the world form, and it prevents the world from collapsing into one shapeless lump, which would be poor design for many reasons, not least because there would be nowhere to put the kettle. This balance is everywhere in materials. In a spring, atoms are arranged so that when the spring is stretched or compressed, the bonds shift away from their preferred positions. The electromagnetic interactions then pull the atoms back toward balance. The spring stores energy in those distorted bonds and releases it when allowed. In rubber, long molecular chains uncoil, shift, and return. In steel, atoms in a lattice resist displacement strongly. In foam, thin walls bend and air pockets compress. All of these behaviors depend on atomic interactions. When we say a material is elastic, stiff, brittle, soft, tough, or flexible, we're describing how its internal electromagnetic architecture responds to being disturbed. That architecture is why a hard object can still deform. Place a heavy book on a table, and the table bends very slightly even if you cannot see it. Stand on a floor, and the floor gives by an extremely small amount. Press your finger on glass, and both your finger and the glass deform, though your finger does so much more. Nothing perfectly rigid exists in ordinary matter. Rigidity is always approximate. Atoms can shift a little. Bonds can stretch a little. The electromagnetic cushion is not an immovable wall. It is more like a very steep resistance. Small changes are possible, but pushing too far requires a lot of energy. The world feels solid because these tiny deformations are limited, and because the restoring forces are strong enough to hold shape. This is also why sound can travel through solids, strike a bell, and the atoms in the metal are displaced slightly from their resting positions. Electromagnetic interactions pull them back and push neighbouring atoms, setting up vibrations that travel through the material. The bell rings because matter is elastic. If atoms were not connected by forces, there would be no coherent vibration, no ringing, no music from strings, no spoken voice carried through air, no creaking floorboards in a quiet house at exactly the moment you hope not to wake anyone. Sound is another way the electromagnetic structure of matter becomes noticeable at human scale. It is touch spread out as a wave. Now, there is an important point about distance. When we talk about the electron clouds of your hand and the table repelling each other, it can sound as if there is a clear measurable gap in the ordinary sense, like a tiny empty slot between two surfaces. At the atomic level, things are less clean than that. Electron clouds are spread out. Their probabilities fade rather than stop sharply. Surfaces are rough. Molecules vibrate. There may be air molecules, water molecules, oils, and other substances between them. So the idea of an exact separation is not as simple as measuring the gap between two books on a shelf. What matters is that the particles do not merge into the same states, and that the forces become strong enough to prevent further approach. The cushion is not a visible space, it is a behaviour. Because of this, even the word contact has levels. In engineering, contact may mean that two surfaces press against each other and transmit force. In chemistry, contact may mean molecules are close enough to react or interact. In atomic physics, the idea of touching becomes less useful, and we speak instead of interactions, potentials, states, and forces. Each language fits its scale. A chef does not need quantum mechanics to say the dough is sticky. A physicist does not need to deny stickiness to explain that it arises from molecular attractions and surface behaviour. Both are true in their proper place. The dough can be sticky enough to ruin your calm morning and still never touch you in the naive sense of atoms as hard balls meeting edge to edge. The electromagnetic cushion also plays a role in why matter can be compressed only so far under ordinary conditions. Push on a sponge and it compresses because its large-scale structure contains air pockets and flexible material. Push on water and it compresses very little because its molecules are already close together and resist being forced closer. Push on steel and it resists strongly because its atoms are arranged in a stiff lattice. In each case, compression means trying to bring particles closer and rearrange their relationships. As the distances shrink, repulsion and quantum effects grow important. Under extreme pressures, such as deep inside planets, matter can be forced into very unusual states. At even greater extremes, inside stars or collapsed stellar remnants, atoms can be stripped, crushed, or transformed in ways far beyond everyday solidity. But in the quiet world of pillows, cups, floors, and hands, electromagnetism maintains the familiar distance. It is strange to realize that the sensation of support is mostly a sensation of refusal. The chair supports you by refusing to let your body continue downward. The floor supports the chair by refusing the chair in the same way. The ground supports the building. The materials inside the earth resist compression. Layer upon layer, matter pushes back. This refusal is not hostile. It is the condition that allows shape, shelter, walking, sleeping, carrying, building, and resting. When you lie in bed, the mattress is not touching you as a collection of tiny solids merging with your body. It's pushing back through electromagnetic interactions arranged across foam, fabric, springs, fibres, and air. The result is comfort. A very large number of invisible refusals can feel, at the human scale, like being gently held. There is a useful everyday demonstration in the simple act of sitting down. Before you sit, gravity pulls your body toward the chair. As you make contact, the chair deforms slightly. Its atoms are shifted from their ordinary positions. Electromagnetic forces inside the chair increase as the material resists this deformation. Your body also deforms, especially soft tissue. Very quickly, a balance is reached. Gravity pulls you down. The chair pushes you up. You feel seated. The experience is calm and simple, but the physical situation is a dynamic balance of forces. Nothing about the chair is passive at the microscopic level. It is continuously responding to your weight. The same idea applies when you walk. With each step, your foot presses against the ground. The ground pushes back. That push is what lets you move. If the ground did not push back, stepping would accomplish nothing. Your muscles press your foot downward and backward, and the electromagnetic resistance of the ground supplies the force that moves your body forward. Walking is not merely you moving over the world. It is the world pushing you along, one step at a time, after you politely shove it first. This is why walking on ice is difficult. The ground is still solid, but friction is reduced so the surface cannot provide the same sideways resistance. It supports your weight, but fails to grip your motion. The electromagnetic interactions are still there, but the surface conditions change how force is transmitted. The cushion is also why two objects cannot occupy the same place in ordinary life. This is so obvious that we rarely question it. A cup sits on a table and not inside it. A key goes into a lock only if the shape permits. A drawer closes only if no spoon has positioned itself in exactly the wrong way, as spoons love to do. At the atomic level, occupying the same place would require the particles and electron structures of two objects to overlap in forbidden or energetically costly ways. The repulsion becomes enormous compared with everyday forces, so objects maintain boundaries. They can touch, press, stick, or break, but they do not simply share volume like two transparent images. Matter has exclusion built into its behaviour, and yet, the world is not just repulsion. If everything only pushed everything else away, there would be no stable matter, no materials, no life, and no blankets, which would be a serious oversight. Attraction is equally important. Electrons are attracted to nuclei. Atoms bond, molecules attract. Water clings to glass. Dust sticks to screens. Paint adheres to walls. Your skin can feel a surface, partly because tiny attractions and deformations create friction and texture. The electromagnetic cushion is not only a wall, it is a zone where attraction and repulsion balance, where closeness becomes possible without collapse. It allows matter to be both separate and connected. This balance is especially clear in chemical bonds. Atoms form bonds when their electron arrangements can settle into a lower energy relationship together. The atoms are not touching as little balls. They're sharing or redistributing electron behavior in a way that makes a stable structure. But if the bonded atoms are pushed too close, repulsion increases. If they're pulled too far apart, the bond may weaken or break. There is a preferred spacing. That preferred spacing gives molecules their shapes. Molecular shape then influences everything from the smell of lavender to the strength of plastic to the structure of DNA. The same rules that help your hand feel a table also help build the chemistry of living things. Touch and life are both downstream of electromagnetic order. In your own body, electromagnetism does even more. Nerve signals depend on electric differences across cell membranes. Muscles contract because electrically controlled chemical processes change the shape and interaction of proteins. Your heart beats through coordinated electrical activity. Your brain works through electrochemical signaling. So the force responsible for the table pushing back is also involved in your ability to feel that push at all. Electromagnetism is both outside and inside the experience. It shapes the object, transmits the pressure, activates the receptors, carries signals through nerves, and helps the brain process the information. If gravity is the great organizer of planets and stars, electromagnetism is the great organizer of everyday sensation. That is why the word cushion is gentle but not weak. The electromagnetic cushion between objects is strong enough to hold up buildings, stop your hand at a wall, let tires grip roads, let tools cut materials, and let a needle pierce skin when force is concentrated enough. It is also delicate enough to produce the softness of fabric, the smoothness of glass, the stickiness of tape, the glide of oil, and the faint brush of a feather. The same basic force can appear as comfort, resistance, damage, warmth, texture, or motion, depending on arrangement. Physics often works this way. A simple rule becomes a vast variety of experiences when repeated through complex structures. So right now, wherever you are, the things touching you are not touching in the old simple sense. They're close enough for their electromagnetic structures to interact strongly with yours. The bed is pushing back, the blanket is resting through a web of molecular forces. The air is pressing through countless collisions. Your clothes are held against your skin by pressure, friction, and sometimes static charge. Even the page of a book or the surface of a phone in your hand is separated from you by a region of interaction too small to notice and too important to ignore. You live surrounded by invisible cushions not soft enough to fall through, not distant enough to feel absent, but perfectly arranged to make the world tangible. And this brings us to a deeper layer of the same story. Electromagnetic repulsion explains much of why matter resists matter, but there is another rule beneath the surface, a quantum rule that makes the resistance even more fundamental. It is not only that electrons dislike being pushed close, because they carry the same charge. It is also that certain particles cannot be arranged in identical ways within the same system. The world has a kind of microscopic seating plan, and electrons are not allowed to all crowd into the same seat, no matter how small the room becomes. To understand why matter has structure, why atoms have layers, why chemistry exists, and why your hand remains your hand when it presses against the table, we have to move from the cushion of electromagnetism into the strange order of quantum rules. Beneath the electromagnetic cushion, there is a deeper kind of order, one that does not behave like an ordinary push or pull. Electrons repel one another because they carry the same electric charge, and that repulsion is already enough to explain much of why your hand does not simply pass through a table, but the story of matter would still be incomplete without one of the strangest rules in quantum physics, a rule that quietly organizes atoms, gives structure to chemistry, helps build the periodic table, and keeps ordinary matter from collapsing into a much smaller and far less useful version of itself. This rule is called the Pauli exclusion principle, named after the physicist Wolfgang Pauli, who gave the universe a kind of microscopic seating plan. It says that certain particles, including electrons, cannot occupy exactly the same quantum state within the same system. In simpler terms, electrons are not allowed to all crowd into the same identical condition, no matter how much they might seem to want the lowest and most comfortable place available. That may sound almost like a rule from a very strict theatre. 1 particle per seat, please. No sharing. No standing in the aisle. No pretending you did not see the ticket number. But in the quantum world, this is not etiquette. It is a basic feature of nature. Electrons belong to a class of particles known as fermions, and fermions follow this exclusion rule. They are not like photons of light, which can pile together in the same state in great numbers, as happens in a laser. Electrons are different. If one electron is already in a particular quantum state, another electron in the same atom cannot simply become an exact copy of it in every relevant way. It must occupy a different state. This one rule is one of the hidden reasons atoms have size, why electrons arrange themselves in layers, why elements have different chemical behavior, and why matter has the firm, structured quality that lets you rest your hand on a pillow without becoming part pillow, which would make getting up in the morning even more complicated than usual. To see why this matters, imagine an atom without the exclusion principle. The electrons around the nucleus are attracted to the positive charge in the nucleus. If there were no restrictions, you might expect all the electrons to settle into the lowest available state, the way tired people might all try to sit in the softest chair in the room. That would make atoms much less varied. Electron arrangements would not build up in layers. Chemical behavior would lose the rich patterns that make one element different from another. Matter would not have the same volume, structure, or stability. The universe would be a much duller place, and not only duller, but unable to support the ordinary complexity we rely on. No familiar chemistry, no stable materials in the same way, no cells, wood, water behavior as we know it, stone, skin, tea, or biscuits. The exclusion principle may sound like a fine technical point, but it is one of the reasons there is a world detailed enough to have furniture in it. In real atoms, electrons fill different allowed states around the nucleus. These states are not little shelves in space, and they are not tiny circular tracks like lanes on a running field. They are quantum patterns, each with its own energy and shape of probability. Some states are closer to the nucleus in energy and structure. Others extend farther out. As more electrons are added, they cannot all occupy the same lowest state, so they fill additional states. This creates shells and subshells, layers of electron behavior that determine how atoms interact. When we talk about an atom having outer electrons, we're talking about electrons in the states most involved in bonding, repulsion, and chemical behavior. These outer electrons are the ones most responsible for what your fingertip encounters when it approaches a table. They're also the ones that decide whether an atom is reactive, inert, metallic, brittle, soft, transparent, salty, or ready to make trouble in a chemistry lab. The exclusion principle is therefore not just a rule about particles avoiding duplication. It is one of the reasons atoms have personality. Hydrogen, carbon, oxygen, iron, gold, silicon, and all the other elements are not different only because their nuclei contain different numbers of protons. They are different because those nuclear charges create different electron arrangements, and those electron arrangements are shaped by quantum rules. Carbon can form strong and flexible bonding patterns because of the way its electrons are arranged. Oxygen behaves the way it does because of its outer electrons. Noble gases are famously unreactive because their outer electron arrangements are already stable, like guests at a party who have found the perfect seat and do not wish to mingle. Metals conduct electricity because some of their electrons are able to move through the material more freely. The details are complicated, but the underlying point is simple. The structure of the everyday world depends on electrons being unable to all do the same thing. This matters for touch because the electrons in matter do not merely repel one another through electric charge. They also resist being forced into arrangements that quantum rules do not allow. When your hand presses against a table, the electron clouds in your skin and the electron clouds in the table are brought very close together. The electromagnetic repulsion increases, but there is also a quantum cost to trying to make electrons occupy the same states or overlap too strongly in certain ways. The exclusion principle helps create the strong resistance that appears when atoms are pushed close. It is part of why matter has volume. It is part of why atoms do not simply collapse into one another. It is part of why solids can exist as stable objects rather than as a vague soup of particles all trying to sink into the same lowest condition. A useful comparison is a room full of people and chairs, though as always with quantum physics, the comparison will eventually start wobbling at the edges. Imagine that everyone in the room is required to sit in a different seat. If more people enter, they cannot all sit on the same chair, even if that chair is nearest the heater and has the best view. They must occupy other seats, spreading out through the room. The room becomes filled in an organized way. Now imagine trying to squeeze the room smaller while keeping everyone inside and still obeying the one person per seat rule. It becomes harder and harder. People must be pushed into more crowded arrangements, higher shelves, smaller corners, increasingly awkward positions near the snack table. In matter, electrons do not occupy literal chairs, but the idea of limited allowed states is useful. Compression is resisted not only because charges repel, but because the available quantum states impose order. Forcing particles into a smaller space changes which states are available and how they must be occupied, and that carries a cost. This is one reason quantum physics feels so different from common sense. In the everyday world, two objects cannot be in the same place because they are solid things with surfaces. In the quantum world, the deeper statement is not really about little hard objects refusing to overlap like pebbles. It is about wave-like states, probability patterns, charges, and rules of occupation. Electrons are not tiny billiard balls painted blue and sent spinning around nuclei. They are quantum entities, and their behavior is described by states that can spread, overlap, combine, and exclude in ways ordinary objects never do. Yet from this strange behavior comes the ordinary fact that your hand stops at the table. The most familiar certainty in the room is supported by one of the least intuitive rules in physics. That is a very typical move for the universe. The Pauli exclusion principle also explains why the periodic table has its layered pattern. The elements repeat certain chemical behaviors because their outer electron arrangements repeat in a structured way as electron states are filled. This is why elements in the same column often behave similarly. It is why sodium and potassium, for example, share certain chemical tendencies, though neither should be invited to a quiet bath without supervision. It is why carbon can build the backbone of life, why silicon is useful in electronics, why helium is stable and floats away from parties with no interest in bonding. The periodic table is not just a list of substances, it is a map of quantum order. Every square on it is, in part, a consequence of electrons obeying the rule that they cannot all occupy the same state. So when you touch a wooden table, you are not only meeting wood, you are meeting the whole history of electron arrangements that make carbon, hydrogen, oxygen, and other atoms form cellulose, lignin, and the complex structures of wood. You are meeting the consequences of quantum rules that made those atoms chemically possible, that allowed the tree to grow, that allowed molecules to form long fibres, that allowed those fibres to harden into material strong enough to become a table. The firmness under your hand is not just a surface effect. It is the large-scale result of a deep ordering principle repeated through atoms, molecules, cells, timber, carpentry, and finally the quiet place where your palm rests. That is a long journey for something we usually describe as touching the table. The same rule helps explain why different elements occupy different amounts of space. As atoms gain more electrons, those electrons must fill different states. They cannot all crowd into the innermost region. The outer structure grows in ways determined by quantum mechanics. This gives atoms their sizes and bonding behaviour. Atomic size is not a hard boundary like the edge of a marble, but atoms do have effective sizes because their electron clouds occupy regions and resist compression. When atoms come together in matter, their effective sizes and bonding preferences shape how they pack. Some form tight crystals, some form loose molecular solids, some make flexible chains, some share electrons across broad metallic structures. The world's textures begin as allowed patterns of electrons. The exclusion principle also operates inside materials when they are compressed. In a solid, atoms are already arranged at distances set by balances of attraction, repulsion, and quantum rules. If you try to squeeze the solid, you push atoms closer than their comfortable spacing. Their electron clouds overlap more strongly. Electric repulsion rises. The exclusion principle increases the resistance to forcing electrons into already occupied patterns. The material pushes back. At the human scale, we call this stiffness, hardness, or incompressibility. At the deeper scale, it is matter defending its quantum organization. A floor under your feet is not merely a passive slab. It is a huge system of atoms maintaining their allowed arrangements, while your weight tries to disturb them. This is true even for things that feel soft. A pillow gives way because its large-scale structure contains fibres, air pockets, and flexible materials that can rearrange. But the atoms within those fibres still obey the same quantum rules. The pillow is not soft because its atoms have relaxed standards. It is soft because its structure can change shape without immediately forcing atoms into strongly forbidden closeness. Once compressed enough, the pillow pushes back too. Even foam has a limit. Even marshmallows, those charming little clouds of sugar and questionable dignity, will resist being squeezed into nothing. Softness is not the absence of quantum order. It is a more flexible arrangement built on top of it. In liquids, the story has another flavour. Water molecules can move around one another, which is why water flows. But each molecule still has a size and shape governed by its electron structure. Water cannot be compressed easily because its molecules resist being forced much closer together. They can rearrange and slide, but they cannot simply overlap. When you put your hand into water, the water moves aside because its molecules are mobile, but you still feel resistance, pressure, and drag. The molecules collide and interact with your skin through electromagnetic forces and quantum restrictions. Water is not solid, but it is still matter, and matter still keeps its distance at the microscopic level. This is why diving badly into water from a height can hurt. Given enough speed, even a fluid can deliver a very firm reminder that its molecules are not interested in being ignored. Gases are more spread out, so they feel much less solid. Air yields easily when you wave your hand through it because its molecules are far apart and can move aside. But even air is not truly penetrable in the sense of having no interaction. Air pressure pushes on your skin all the time. Molecules strike you constantly. If you move fast enough, air resistance becomes strong. Put your hand out of a car window and you feel the wind press against it. Increase speed far enough and air can become a fierce opponent. The same matter that seems almost absent in a quiet room can push hard against an airplane or heat dramatically around a spacecraft returning to Earth. State, density and motion matter But the underlying particles still obey quantum rules. Even the gentlest breeze is made of atoms and molecules that cannot simply vanish into one another. The exclusion principle becomes even more dramatic in extreme places. In ordinary solids, electromagnetic repulsion and quantum structure create familiar firmness. In certain stars, after they exhaust their fuel, matter can be compressed so intensely that ordinary atomic structure is broken down. Electrons are squeezed into a dense state where their refusal to occupy the same states creates a pressure strong enough to help support a white dwarf star against gravity. This is called degeneracy pressure, though the name sounds less like an astrophysical principle and more like a complaint about modern television. In such stars, the exclusion principle is no longer just helping hold up tables and chairs. It is helping hold up a stellar remnant with a mass comparable to the Sun compressed into a body roughly the size of Earth. The same rule that contributes to the firmness under your fingertips also helps decide the fate of stars. Physics enjoys reusing its best ideas at wildly different scales. Push even farther, and in neutron stars, related quantum rules involving neutrons become important under conditions more extreme than anything in ordinary life. Matter. There is so dense that a small amount would have an enormous mass. These objects remind us that the principles behind solidity do not stop at furniture. They extend into the life cycles of stars and the structure of the universe. But for tonight, we do not need to travel all the way to a neutron star to appreciate the point. The rule that keeps certain particles apart is already present in your hand, your pillow, your bones, your blanket, and the floor. It is quiet in daily life because it is working properly. Like good plumbing, good physics often becomes noticeable only when we start asking why everything is not going terribly wrong. There is another important detail. The exclusion principle is not a force in the same simple sense as electromagnetism. It does not push with a field the way electric charges do. It is a rule about the allowed states of identical fermions. Yet it produces effects that feel force, like when matter is compressed. This can be hard to picture because our everyday language is built around pushes and pulls. Quantum rules are not always pushes and pulls. Sometimes they are restrictions on what arrangements can exist. If you try to create a forbidden arrangement, nature does not allow it. The result at larger scales can appear as pressure or resistance. So when your hand presses into a surface, the resistance you feel comes from both ordinary electromagnetic interactions and this deeper quantum refusal of electrons to be arranged improperly. The surface is not making a decision, of course. It is simply behaving according to the rules that all electrons follow. This is where the feeling of solidity becomes especially interesting. A table seems hard because it resists deformation, but the resistance is not caused by little pieces of matter being absolutely full. It is caused by charge interactions and the limited availability of quantum states. The atoms of the table occupy space because their electrons have spread out into allowed arrangements around nuclei, and because forcing those arrangements to overlap with the electrons in your hand is energetically and quantum mechanically costly. This is what gives ordinary objects their effective volume. The table is not solid because it is dense with tiny hard pellets from edge to edge. It is solid because its electrons and nuclei form a stable quantum structure that other matter cannot simply invade. That idea also helps answer a question that often follows from atomic emptiness. If most of the atom is space, why can the electrons not just move aside and let another atom through? Sometimes, in certain conditions, particles can pass through barriers in ways that seem impossible from a classical point of view. Quantum tunneling is a real phenomenon. It is important in nuclear processes, electronics, and many areas of physics. But for a whole hand passing through a whole table, the situation is not remotely comparable. Your hand is not one particle approaching a simple barrier. It is an enormous warm biological structure made of vast numbers of atoms, all interacting with vast numbers of atoms in the table. The coordinated quantum event required for your hand to pass through without disruption is so fantastically unlikely that for practical purposes it will not happen. You can wait with your hand on the table for longer than the age of the universe, and the table will continue to be disappointingly table-like. This is another way scale protects ordinary experience. Quantum mechanics allows strange things, but not every strange possibility becomes a meaningful everyday event. Individual particles can behave in ways that would be astonishing for large objects. Large objects are made of huge numbers of particles interacting with their environments, and those interactions make ordinary behavior stable. The table stays put. Your hand stays your hand. The boundary between them remains firm. Quantum weirdness does not vanish, but it becomes organized into the reliable patterns of the everyday world. It is still there underneath, like a complicated backstage crew making sure the calm stage performance continues. The exclusion principle also helps explain why matter does not collapse under its own electric attractions. Electrons are attracted to nuclei. Without quantum mechanics, one might wonder why electrons do not simply fall into the nucleus. The full answer involves the wave nature of electrons, allowed energy states, and the structure of quantum theory, but the key idea is that electrons in atoms occupy stable states. They are not little planets losing energy as they orbit. They do not spiral inward in the classical way. Their allowed states give atoms structure. The exclusion principle then determines how multiple electrons can occupy those states. Together, these quantum rules keep atoms stable, and stable atoms make stable matter possible. The table, the chair, the blanket, and your own body are all beneficiaries of this deep atomic stability. It is easy to take stability for granted because it is so constant. A cup remains a cup from one moment to the next. Your hand does not need to be rebuilt every second from first principles, which is considerate of it. But at the microscopic level, stability is an achievement. Charged particles attract and repel. Electrons behave as waves and particles in ways that defy simple pictures. Nuclei contain protons that repel one another electrically, but are held together by another force at very short ranges. Thermal motion shakes atoms and molecules. Radiation passes through. Chemical reactions are possible, and yet matter persists. Your skin remains skin. A wooden table remains wood. A stone remains stone. Quantum rules are part of the reason the world is not a chaotic blur. There is a pleasant irony here. Quantum mechanics has a reputation for making reality seem uncertain and strange. And it does. It tells us that particles do not have all the definite properties we might expect, that measurement matters, that probabilities are fundamental, that tiny things can behave in ways that no chair would ever dare. But quantum mechanics is also what makes ordinary stability possible. It is the reason atoms have structure. It is the reason chemistry has patterns. It is the reason matter can be firm. The very theory that seems to loosen reality at the smallest scales helps build the dependable world at our scale. Quantum physics is not only weirdness, it is also the hidden source of everyday reliability. It is the reason the floor has not become a vague suggestion. This should change how we think about the word empty. Atoms are mostly empty by volume, but quantum rules make that emptiness structured. Electrons occupy states that extend through space. They do not fill the atom like pudding in a bowl, but their presence shapes how the atom behaves. The space around the nucleus is not a vacant storage area. It is an organized quantum region. When atoms combine, these regions interact. When matter is compressed, the allowed states shift. When surfaces approach, electrons resist being forced into forbidden arrangements. So the empty space of matter is not a weakness. It is a rule-governed openness, a place where structure exists without being solid in the simple sense. You can feel the result right now. The surface beneath you has not collapsed. Your body has not passed through it. Your clothes remain outside your skin rather than merging into you, molecule by molecule. Your fingers can press together and stop. Your tongue can feel the shape of your teeth. Your eyelids can close over your eyes with astonishing gentleness, each surface interacting without becoming the other. All of this is ordinary only because the underlying physics is so consistent. The rules do not take a night off. The exclusion principle does not become tired and let electrons share identical states, because everyone seems sleepy. Nature is very strict about this, which in this case is a blessing. This strictness is also why atoms can stack into larger forms without losing individuality completely. In a solid, atoms may be bound together, but they still occupy roles in the structure. Their electron states combine and influence each other, forming the electronic properties of the material. In metals, this produces bands of states through which electrons can move, making conductivity possible. In insulators, electrons are more tightly bound, so electric current does not flow easily. In semiconductors, the arrangement sits between these extremes, allowing the control of current that makes modern electronics possible. The exclusion principle is built into all of this. Your phone, your lamp, your computer, and countless modern devices depend on quantum rules that also help keep matter apart. So when a screen glows in your hand, the same broad quantum order that prevents your hand from passing through the device also helps the device function. The universe is economical with its principles, even when the technology is not economical with battery life. The rule also helps explain why chemistry is not random. Atoms bond in particular ways because electron states have particular structures. Some atoms prefer to gain, lose, or share electrons to reach more stable arrangements. Molecules have shapes because electrons arrange around nuclei in allowed patterns. Those shapes determine how molecules fit together, react, twist, fold, and build larger structures. Proteins fold into working forms. DNA holds information through molecular pairing. Water has properties that make life possible because of its electron distribution and molecular shape. The exclusion principle is not the only rule involved, but it is part of the foundation. Matter keeps its complexity because electrons must arrange themselves in ordered, differentiated ways, and from all of that complexity comes touch. Not immediately, of course. There are many steps between an electron state and the feeling of a blanket. Atoms form molecules. Molecules form fibers. Fibers form fabric. Fabric presses against skin. Skin deforms. Receptors respond. Nerves transmit signals. The brain interprets them, but the chain reaches all the way down. If electrons did not obey quantum rules, atoms would not have the structures required for familiar materials. If matter did not resist overlap, surfaces would not provide pressure. If surfaces did not provide pressure, touch as we know it would not exist. Your sense of the world begins in the rules of particles that you will never see directly. This is why the idea that nothing truly touches should not make contact feel empty or false. In fact, touch is made possible by separation. The exclusion principle preserves the distinction between one piece of matter and another. Electromagnetic interaction communicates across the tiny boundary. Together they allow closeness without collapse. That is what touch is. Not merging, not simple collision, but nearness held in tension by rules. When you hold someone's hand, the atoms do not fuse into a single object. The surfaces remain distinct. The pressure, warmth, texture, and emotion arise because two bodies come close enough for forces to pass information between them while still remaining themselves. Physics may sound unromantic at first, but it quietly protects the possibility of closeness. Without separation, there is no touch. Without resistance, there is no feeling of being held. So the next time your fingertips rest on a surface, imagine not a hard edge meeting, another hard edge, but a vast number of electrons maintaining their allowed order. Imagine the outer regions of atoms approaching, resisting, adjusting, and settling into balance. Imagine matter refusing to be compressed into forbidden sameness. The sensation is simple because your body needs it to be simple, firm, soft, smooth, warm, safe, sharp. But underneath each word is a quantum rule being obeyed everywhere at once. The world feels solid because its smallest constituents are not free to behave any way they please. And that brings us closer to the human side of the question. The forces and rules explain why surfaces resist and why matter occupies space, but they do not yet explain how resistance becomes experience. Somewhere between electron clouds and conscious awareness, pressure must be converted into sensation. The skin must detect deformation. Nerves must carry signals. The brain must turn patterns of electrical activity into the feeling of a chair beneath you, a blanket over you, a cup in your hand, or the faint brush of air across your face. The physics keeps matter apart, but biology turns that separation into touch. And this is where the story becomes wonderfully personal, because until now we have been speaking mostly about matter itself. Atoms, electrons, repulsion, quantum rules, the hidden refusal that keeps one object from simply sliding into another. But none of that by itself explains the feeling. A table could push back against a hand in perfect obedience to physics, and still there would be no touch unless a living body noticed it. The world can resist you, but sensation begins only when that resistance is translated into the language of nerves. Somewhere between the electron clouds of a wooden surface and the quiet awareness in your mind, an invisible physical push becomes pressure, texture, warmth, softness, and shape. The universe knocks very gently on the door of the skin, and the nervous system answers. Let us begin with a simple moment. Imagine resting your fingertips on a blanket. Nothing dramatic happens. There is no spark, no thunderclap, no announcement from the atoms. The blanket gives way slightly. The skin of your fingertips changes shape. Tiny ridges and valleys in your fingerprints meet the woven structure of the fabric. Some parts of the skin are pressed more than others. Some parts stretch. Some parts feel warmth. Some parts feel the faint drag of fibers as you move. At the atomic level, the electrons in the molecules of your skin and the molecules of the blanket are resisting overlap through electromagnetic interaction. At the tissue level, that resistance becomes mechanical pressure. At the biological level, pressure becomes a signal. At the level of awareness, the signal becomes the thought, or perhaps not even the thought but the quiet certainty, that you are touching a blanket. Your skin is not just a covering, it is an organ of perception, a living landscape filled with sensors. It protects you, holds you together, helps regulate temperature, and gives the world a way to speak to your nervous system. It is sensitive enough to detect a light breeze, a small vibration, the difference between silk and paper, the coolness of metal, the warmth of a mug, and the alarming precision of a crumb in the bed. It is also tough enough to handle pressure, friction, weather, and the occasional collision with a door frame that seemed, until that moment, to be farther to the left. The skin has to perform a difficult balancing act. It must be sensitive, but not so sensitive that every sock becomes a crisis. It must be protective, but not so numb that you fail to notice danger. It must notice the world without being overwhelmed by it. Inside the skin are many kinds of sensory receptors. Some respond to steady pressure, some respond to light touch, some respond to vibration, some notice stretching, some detect heat or cold. Others warn you of damage, or possible damage through pain. They are not all sitting at the same depth, and they are not all built for the same task. Some are near the surface, ready to notice delicate changes. Others are deeper, responding to stronger pressure or vibration that travels through the tissue. This layered arrangement lets your body read touch in more than one way at once. When you hold a cup, you are not receiving a single message that says cup. You're receiving many streams of information. Pressure at the fingertips, curvature against the palm, smoothness at the surface, warmth passing into the skin, weight pulling down through the muscles, slight adjustments as your grip changes. The brain gathers all of this and gives you one simple experience. You are holding a cup. Very clever. Also, please do not spill it. The first step in touch is deformation. That is a plain word for something being changed in shape. When an object presses against your skin, It slightly bends, compresses, or stretches the tissue. The atoms of the object never need to truly touch your atoms in the old simple sense. The electromagnetic repulsion between the surfaces creates force, and that force changes the shape of the skin. Sensory receptors are built to respond to those changes. Some receptors have tiny structures that open or change when the surrounding tissue is pressed or stretched. This allows charged particles to move across the membrane of the nerve ending, changing its electrical state. If the change is strong enough, the nerve sends a signal. A physical push has become an electrical message. The hand has begun to speak to the brain. That phrase, electrical message, is not just a metaphor. Nerve cells operate through electrical and chemical changes. They maintain differences in charge across their membranes, and when stimulated, they generate travelling pulses that move along the nerve fibre. These pulses are not like electricity flowing through a copper wire in quite the same way. They are biological waves of changing membrane state, passed along through the movement of charged particles and the opening and closing of tiny channels. But they are electrical in the broad sense, and they depend on the same fundamental electromagnetic reality we have already been discussing. So the force that keeps your skin from merging with the table is related in a deep physical way to the signal that tells your brain the table is there. Electromagnetism is on both sides of the experience, outside in matter and inside in nerves, like a stagehand who also plays the violin. Once the signal begins, it travels from the skin through nerves toward the spinal cord and then up to the brain. Different kinds of touch information travel along different pathways. Some signals move very quickly, especially those that help you respond to sudden pressure, vibration, or pain. Others travel more slowly. Your nervous system is organized not merely to notice touch, but to make touch useful. If something sharp presses into your foot, you do not want a thoughtful essay from the nervous system 3 minutes later. You want the leg to move, quickly. This is why some responses are handled partly by reflex circuits in the spinal cord before the brain has fully processed the details. Your body can pull away from danger before you have finished forming the sentence. What on earth was that? For gentler touch, the brain has time to build a richer picture. Signals from the skin eventually reach areas of the brain that map the body. There is a region called the somatosensory cortex, which receives information about touch, pressure, vibration, temperature, and body position. The map in this part of the brain is not drawn according to the size of body parts, but according to sensitivity and control. The hands, lips, tongue, and face occupy large regions because they are richly sensitive and important for interaction. Your fingertips, in particular, are marvels of tactile resolution. They can detect tiny differences in texture and shape, partly because they have many receptors packed close together, and partly because the brain devotes significant processing power to them. Your back is less precise. This is why you can tell exactly where a crumb is under one fingertip, but if someone lightly touches your upper back, you may only know the general district in which the event occurred. The brain does not simply receive touch like a passive screen, it interprets it. It compares signals. It uses memory, expectation, movement, and context. If you run your fingers over a surface, your brain combines tactile information with motor information about how your fingers are moving. This active exploration is called haptic perception. It is how you can reach into a pocket and recognize a key, a coin, or a folded receipt without looking. Your fingers move, the object resists, the skin deforms, joints shift, muscles report position, and the brain constructs the object's shape. Touch is not only something that happens to you. Often, it is something you do. You investigate the world with your hands, and the world answers through resistance. This is why a still touch and a moving touch feel different. Rest your finger on a smooth surface, and you may feel pressure and temperature. Slide your finger across it, and texture becomes clearer. Tiny surface features create vibrations in the skin. The pattern of those vibrations tells the brain about roughness, grain, and friction. Some tactile receptors respond especially well to vibration, which makes them important for reading fine textures. When you feel the difference between paper and polished wood, part of that difference is the way each surface produces tiny fluctuations as your skin moves across it. At the atomic and molecular level, electromagnetic interactions create friction and resistance. At the skin level, that resistance becomes vibration and deformation. At the brain level, it becomes texture. A surface is translated into a feeling by motion. Fingerprints help with this process. They are not only there to make detective stories more complicated. The ridges on your fingertips may help improve grip and influence how vibrations are generated when you slide over surfaces. They also help channel moisture and change the mechanical interaction between skin and object. Your fingertips are not smooth rubber pads. They are textured instruments. When they pass across fabric, glass, wood, or skin, the ridges shape the contact and help create patterns your receptors can detect. The little whirls and loops that identify you also help you feel the world. Your identity, at least in one small sense, is pressed into every touch. Pressure is only one part of the experience. Temperature adds another dimension. When you touch a metal spoon and it feels cold, the sensation comes from heat leaving your skin quickly. The spoon may be at the same room temperature as a wooden spoon, but metal conducts heat away faster, so your cold receptors respond more strongly. When you touch a warm mug, energy flows into your skin and warmth receptors respond. Temperature receptors do not simply tell the brain the exact temperature of an object. They are sensitive to changes in energy flow. This is why the same room can feel chilly after a warm bath and comfortable after coming in from the cold. The body measures the world through comparison, not through detached scientific neutrality. Your skin is more like a practical advisor than a laboratory thermometer. It is not interested in perfect data. It wants to know whether you should keep holding the mug. Pain is another layer, and it is not merely intense touch. Pain has its own pathways and receptors, designed to warn of possible or actual damage. A sharp point creates concentrated pressure that can deform or break tissue. Extreme heat or cold can damage cells. Harsh chemicals can irritate or injure. Pain receptors respond to these threats and send signals that the brain interprets as urgent. Pain is unpleasant for good reason. It is the nervous system becoming difficult to ignore. From the standpoint of physics, the sharp object is still interacting through forces. From the standpoint of biology, the force is too concentrated for the tissue to tolerate. From the standpoint of the person stepping barefoot on a stray piece of something in the dark, the philosophical distinctions can wait until after the hopping and muttering have ended. Soft touch, on the other hand, can be deeply calming. A gentle stroke on the skin activates receptors associated not just with detecting pressure, but with social and emotional touch. Human skin is not only a measuring device for objects, it is also part of bonding, care, comfort, and communication. A hand on a shoulder, a hug, a pet leaning against you, the weight of a blanket. These sensations can influence mood and nervous system state. The physics may begin with repulsion between electron clouds, but the experience can become reassurance. Matter resists matter, and somehow the brain interprets certain patterns of that resistance as kindness. That is one of the more beautiful escalations from atomic physics to human life. The brain also filters touch constantly. Right now, there are probably many sensations you are not noticing until invited to notice them. The pressure of clothing, the contact of your feet with the floor, the position of your tongue, the air on your skin, the weight of your body against a chair or mattress. The brain reduces the volume on familiar steady signals so you can pay attention to changes. This is called adaptation. Put on a watch, and at first you feel it clearly. After a while it fades into the background. The receptors and brain become less responsive to an unchanging stimulus. This is useful. Otherwise, the entire day would be one long announcement that socks exist. But adaptation can also make touch interesting. A sensation that disappears can reappear when something changes. Shift in your chair and suddenly pressure becomes noticeable. Move your sleeve and fabric returns to awareness. A blanket that felt neutral can become comforting when you settle under it. The brain is not recording every contact equally. It is highlighting difference, change, and relevance. Touch is therefore not a perfect map of physical pressure. It is a living interpretation shaped by attention. Attention can alter touch in surprisingly powerful ways. If you focus on your hand resting on a table, the sensation becomes more detailed. You may notice warmth, pressure, tiny shifts, the pulse in your fingers, perhaps even the faint texture beneath the skin. If you become absorbed in a conversation or a story, the same hand may vanish from awareness until it tingles or you move it. The physical contact did not stop. The signals did not disappear completely. But the mind changed how much importance they were given. Touch, like time, has a subjective side. It is grounded in physics and biology but shaped by attention. Expectation matters too. If you believe something will be cold, sharp, soft, or unpleasant, the brain may prepare for that experience. This can influence how touch is perceived. A harmless object may feel more alarming if you think it is dangerous. A gentle pressure can feel comforting in one context and irritating in another. The same hand on your shoulder may feel reassuring if it belongs to someone trusted and startling if unexpected. Touch is never merely pressure. It arrives with meaning. The skin reports the event, but the brain asks who, what, where, why, and should we be concerned? This is why illusions of touch are possible. A classic example involves crossing two fingers and touching a small object between them. The brain may interpret the sensation as two objects instead of one, because the usual map of finger positions has been confused. Another example is the rubber hand illusion, where a person can begin to feel as though a fake hand belongs to them if their real hidden hand and the fake hand are stroked in matching ways. The brain combines vision and touch to decide what is part of the body. When the signals line up, the sense of ownership can shift. This may sound like a party trick, but it reveals something deep. The feeling of touch is constructed. It is not made up from nothing, but it is assembled from signals, body maps, expectations, and context. Your sense of body position also contributes to touch. This sense is called proprioception. It tells you where your limbs are without needing to look. If you close your eyes and touch your nose, your brain knows where your finger is moving because muscles, tendons, and joints contain sensors that report stretch and position. When you feel an object, the brain combines skin sensation with proprioception. This is how you know not only that something is pressing on your finger, but where your finger is in space and how the object is shaped. Without proprioception, touch would be far less useful. You might feel pressure but struggle to locate it in the moving architecture of your own body. The brain needs both the surface report and the body map. The feeling of weight is another blended experience. When you hold an object, touch receptors in the skin detect pressure, but muscles and tendons also report the force required to support it. Your brain combines these signals to judge heaviness. That is why an object's weight can feel different depending on its size and expectation. A small object that is unexpectedly heavy feels surprising. A large object that is unexpectedly light feels almost suspicious, like a suitcase that has forgotten its purpose. The sensation of weight is not just the object pressing into your skin, it is your whole body estimating effort, pressure, balance, and expectation. This blending is especially clear in tools. When you use a spoon, pen, walking stick, or toothbrush, your sense of touch extends through the object. You can feel the hardness of food through a fork, the texture of paper through a pen, the ground through a cane. Strictly speaking, the receptors are still in your skin and body. The tool itself has no nerves. But vibrations and forces travel through the tool into your hand, and the brain learns to interpret them as information about the world beyond the skin. The boundary of felt experience expands. A blind person using a cane does not merely feel the handle. Through practice, the brain can interpret taps and vibrations as information about surfaces and obstacles at a distance. Touch becomes extended through matter. The electromagnetic interactions at the far end of the cane travel as mechanical vibrations through the object, into the hand, and into awareness. The world reaches you by a chain of resistance. That chain can be very delicate. Consider reading Braille. The raised dots are small, but fingertips can detect their patterns through finely tuned touch receptors and careful movement. The skin deforms over each raised point. Signals travel to the brain, meaning emerges. The physical height of the dots becomes language, or think of a musician feeling the strings of an instrument. The finger detects tension, vibration, and position. The musician adjusts pressure and movement with extraordinary precision. At every moment, touch guides action. Repulsion between matter becomes art through the body's ability to sense and control it. There is a similar elegance in the mouth. The tongue and lips are extremely sensitive. They can detect tiny textures in food, temperature changes, pressure, and shape. This helps with eating, speech, and expression. The texture of food is a major part of flavour, even though we often think of taste and smell first. Crispy, creamy, gritty, chewy, smooth, dry, fizzy. All of these are tactile experiences. When you sip tea, the warmth, fluid motion, and contact with the mouth are part of the experience. When a biscuit is too dry, touch reports the situation with admirable honesty. Eating is not just chemistry on the tongue. It is touch, temperature, smell, sound, and memory arriving together. The skin itself is not uniform. The fingertips are highly sensitive, the lips even more so, while the forearm, back, and thigh detect touch more broadly. This uneven sensitivity matches the needs of the body. Hands explore and manipulate. Lips and tongue help with speech and food. The back mostly needs to know whether something is pressing, scratching, cold, warm, or possibly a cat deciding to settle in. The brain's touch map reflects these priorities. The body's not designed as a general scientific instrument. It is designed by evolution to survive, move, eat, bond, avoid harm, and occasionally locate a dropped coin by patting around under the sofa. When we connect this biology back to atomic physics, the full chain becomes almost absurdly rich. The electrons in an object repel the electrons in your skin. That repulsion creates force. The force deforms tissue. The deformation activates receptors. The receptors generate electrical signals. The signals travel through nerves. The brain processes them alongside body position, memory, attention, and expectation. The final result is a feeling. A smooth table, a soft blanket, a cold spoon, a warm hand, a rough wall, a sharp edge. What began as a rule of matter becomes part of your inner life. It is tempting to ask where, exactly, touch happens. Is it at the surface of the object, in the skin, in the nerves, in the brain? The honest answer is that touch is a process spanning all of these. The physical interaction begins at the boundary between your body and the world. The biological signal begins in sensory receptors. The conscious experience arises in the brain. Remove the object and there is no external touch. Remove the receptors and the pressure is not detected. Remove the brain's interpretation and there is no felt experience. Touch is not located in one simple place. It is a relationship between matter, body, and awareness. This relationship can continue even when a limb is gone, as in phantom limb sensations. Some people who have lost a limb still feel touch, pain, or position in the absent limb. This happens because the brain's body map can remain active even when the physical limb is no longer there. The experience may be vivid and real to the person feeling it. This shows that touch is not just raw input from skin. The brain plays an essential role in creating the body as we feel it. The physical world normally guides that creation. but the brain's maps and predictions can generate sensations even without ordinary contact. Touch is grounded in matter, but lived in the nervous system. On the gentler side, this is also why imagined or anticipated touch can affect us. Thinking about a soft blanket may make you aware of comfort. Watching someone touch a rough surface may almost make you feel its texture. Seeing a needle approach skin can make people flinch before anything happens. The brain is predictive. It does not wait passively for the world. It prepares, simulates, and interprets. This helps you respond quickly, but it also means perception is always partly constructed. What you feel is not a simple copy of the outside world. It is the brain's best useful version of what is happening to the body. Still, the outside world matters, very much. If you press your hand onto a surface, the pressure is real, the atoms are resisting, the skin is deforming, the nerves are firing, the brain is interpreting. The fact that touch is constructed does not make it imaginary. A house is constructed too, and people still prefer one with a roof. The sensation of touch is built from parts, but it is a real event in a living system. It is how physics becomes experience. This is perhaps the most important point. When scientists say that atoms do not truly touch, they are not saying touch is fake. They are saying touch is not what it first appears to be. It is not the direct meeting of tiny solid surfaces. It is the detection of forces. Your body has learned, through evolution and development, to translate those forces into a practical, meaningful world. The brain does not tell you about electron repulsion, because that would be far too much information and not very helpful while carrying soup. Instead, it tells you the bowl is hot, the handle is smooth, grip more carefully. Sensation is physics simplified for survival. And what a good simplification it is. Touch lets you move through the world without needing to calculate it. You can button a shirt, turn a page, wash a cup, tie a shoelace, stroke a pet, open a door, adjust a pillow, and find the edge of a blanket in the dark. These acts depend on the body's ability to turn invisible repulsion into useful feeling. If the brain had to understand every electron interaction consciously, even picking up a spoon would become an all-day project, and dinner would be very late. So the feeling of touch is a kind of translation. The language of atoms is force, charge, motion, probability, and restriction. The language of the skin is pressure, stretch, vibration, warmth, and pain. The language of the brain is object, texture, comfort, danger, and meaning. Each level translates the one below it into terms the next level can use. Nothing is lost exactly, but much is simplified. The full atomic detail becomes a human world of surfaces. That is why you can rest your hand on a table and feel not a storm of microscopic events, but simply a table. Calm, firm, present. There is a quiet kindness in that. The universe does not present itself to you as endless raw data. It arrives filtered through senses shaped to help you live. Touch gives you the world in a form you can trust most of the time. It tells you where your body ends and the rest of reality begins, even though physics says that boundary is not a hard line but a region of interaction. It tells you what can support you, what can harm you, what can warm you, what can comfort you. It turns the refusal of matter into the reassurance of contact. Right now, as you listen, your skin is performing this translation without effort. The surface beneath you is pushing back through electromagnetic and quantum rules. Your tissues are slightly compressed. Receptors are responding or adapting. Signals are travelling and fading. Your brain is keeping only what seems important. Perhaps the blanket has disappeared from attention until this sentence brings it back. Perhaps your shoulders have softened. Perhaps the chair beneath you now feels a little more noticeable, not as a simple object touching you, but as a vast atomic structure pressing back in a way your nervous system can understand. And from here, the next layer of the story begins to open. Because once repulsion becomes sensation, the details of the material begin to matter. The same basic physics can feel like velvet, stone, water, glass, skin, wool, metal, or warm bread. A soft surface and a hard surface both keep your atoms apart, but they do so with very different kinds of structure. Your body reads those differences as the texture and firmness of the world. So the question becomes not only why touch exists, but why it feels so varied, why one thing yields and another resists, why a pillow receives you gently while a stone answers with almost no patience at all. Now that we have followed touch from invisible forces into the nervous system, we can return to the familiar world with a slightly stranger kind of attention, because the world does not merely feel solid, it feels solid in many different ways. A pillow gives way beneath your head, a stone refuses your hand almost immediately, skin is soft and warm, glass is smooth and cool, wood is firm but not quite like metal, rubber grips, silk glides, sand shifts, water flows, clay yields and stays changed. Each of these sensations seems obvious while you feel it, but each is a different solution to the same hidden question. How does matter respond when other matter tries to move into its space? At the deepest level of ordinary contact, the same rules are always present. Atoms approach atoms, electrons resist overlap, quantum rules preserve structure, forces pass through materials, skin deforms and nerves report. But the way those rules are arranged differs wildly from one substance to another. That is why touching a feather does not feel like touching a brick, even though both are made of atoms that obey the same basic physics. The difference is not in whether matter truly touches. The difference is in how easily the material changes shape, how its surface is arranged, how energy travels through it, how strongly its molecules hold together, and how your body interprets the result. Solidity is not one thing. It is a whole family of behaviours wearing the same everyday name. Let us start with skin, because it is both the thing that touches and the thing that is touched. Skin feels soft because it is a living layered material filled with water, cells, fats, proteins, tiny blood vessels, nerves, and flexible structures that can move and compress. Press your fingertip into your palm and the surface changes shape. It yields. The tissue spreads and rebounds. Blood shifts. The layers underneath respond. Yet it does not behave like a liquid, because its cells and fibres are organised into a stable structure. It is not hard like bone, not flowing like water, not fibrous like cloth, though it contains elements of all these ideas in its own biological way. Skin is soft because its internal architecture allows deformation while still maintaining integrity. It gives, but it does not give up. A stone, by contrast, is hard because its atoms and minerals are arranged in structures that resist deformation strongly. Press your finger against a stone and the stone changes shape far less than your skin does. The force of your press still affects it, but the change is extremely small. Your skin flattens against the stone, not because the stone is an absolute wall, but because your tissue is much easier to deform. The stone's atoms are locked into mineral patterns that do not casually rearrange. To change them significantly, you would need much more force, perhaps enough to scratch, chip, crack or break the stone. At gentle pressure, the stone answers almost immediately with resistance. Your brain calls this hard. This means hardness is not simply a measure of how solid something is. It is a measure of how a material resists certain kinds of change. Some materials resist scratching, some resist compression, some resist bending, some resist breaking. These are related but not identical. Glass is hard in the sense that it resists scratching and deformation, but it can shatter because it does not easily absorb and redistribute stress once a crack begins. Rubber is soft compared with glass, but it can stretch and recover without breaking. Steel is hard and tough in many situations, though it can bend under enough force. A diamond is famously hard, but hardness does not mean indestructible. The word solid in daily life hides all these differences under one blanket, and then material science quietly lifts the blanket and finds a very complicated room underneath. The feeling of softness often comes from a material's ability to spread force over time and space. A pillow feels soft because it deforms around you. Your head presses down, and the pillow's fibres, foam, feathers, or filling rearrange. Air may move inside it. The pressure is distributed across a wider area, and the force rises gradually. Your skin and deeper tissues experience a gentler transition. A stone does not do this much. The contact area may be smaller, the pressure more concentrated, and the resistance more immediate. Your body feels the difference as comfort or firmness. The atoms in the pillow are not more willing to merge with you. They are simply arranged in structures that can shift before resisting strongly. This is why a mattress can support you even though it feels soft. A good mattress is not one that offers no resistance. It is one that offers resistance in a carefully distributed way. Too little resistance, and you sink uncomfortably. Too much, and it feels like sleeping on a polite section of pavement. The comfort comes from a balance between yielding and support. At the microscopic level, the materials inside the mattress are still resisting compression through the same physical principles, but the large-scale structure gives them room to respond gradually. Softness is not the absence of solidity. It is solidity with patience. Human skin has its own version of this patience. When you touch another person's hand, the sensation is not like touching wood or stone because living tissue deforms, warms and moves. Skin has moisture, texture, elasticity and temperature. It is supported by softer tissue underneath, and its surface is constantly renewing. The warmth matters because temperature is part of touch. The slight give matters because pressure is spread. The texture matters because fingerprints, pores, fine hairs, and tiny surface features shape the interaction. The emotional meaning matters too because the brain does not treat all contact as neutral. A handshake, a hug, a medical examination, and being poked in the ribs may involve similar physical categories of pressure, but the experiences are not the same. Matter provides signals. The brain gives them context. Stone has context too, though not emotional context of its own, as far as we can tell, which is a relief for anyone who has ever skipped one across a pond. A stone feels cool because it often conducts heat away from your skin faster than surrounding air or fabric. It feels hard because it resists deformation. It may feel rough because its surface has grains, cracks, or irregularities. It may feel smooth if worn by water over time. All of these properties come from structure. A river stone and a piece of broken granite may have similar mineral origins in a broad sense, but the surfaces tell different stories. One has been polished by long contact with moving water and sediment. The other has fresh edges and fractures. Your fingers can read these histories through touch, not as dates or events, but as texture. The illusion of solidity becomes clearer when we compare materials that seem solid but behave differently over time. Honey in a jar holds its shape for a moment, then slowly flows. Clay can be shaped by a hand and remain changed. Wax softens with heat. Ice feels hard but melts into water. Glass feels rigid, while rubber bends and returns. All of these are made of atoms and molecules interacting through electromagnetic and quantum rules, but their internal arrangements respond differently to stress and temperature. A solid, at our scale, is a material that maintains its shape over the time scale and conditions we care about. Change the temperature, the pressure or the time allowed, and the behavior may change. Solidity is not just a property of matter, it is a relationship between matter, force, and time. This is why heat can make firm things soften. Warm butter yields under a knife. Cold butter resists and may tear the bread, a small domestic tragedy known to breakfast everywhere. The atoms and molecules in warm butter have more thermal motion, and the structures holding it firm are easier to rearrange. Metal heated enough can soften and glow. Plastic can bend. Wax can melt. At lower temperatures, materials may become stiffer or brittle. The same substance can feel very different depending on how much energy its molecules have. Temperature changes the internal motion of matter, and internal motion changes how matter responds when touched. The object is not simply soft or hard in isolation, it is soft or hard under particular conditions. Water gives us another useful contrast. Put your hand in water, and it does not stop you the way a tabletop does. It moves aside, yet it still touches you. You feel pressure, coolness or warmth, drag and flow. Move your hand slowly, and water yields smoothly. Move it quickly, and resistance grows. Jump badly into water from a height, and it can feel shockingly hard. The water molecules are not locked into a rigid structure like a crystal, but they still resist being moved abruptly because they have mass, interact with one another, and must be displaced. At low speed, they can rearrange. At high speed, they cannot get out of the way quickly enough. Softness and hardness again depend on the interaction. Even water can be firm if you meet it rudely. Air is gentler still, but not absent. You move through it easily because its molecules are far apart and mobile. Yet wind can push strongly. A storm can bend trees, lift roofs, and make a quiet walk feel like a negotiation with an invisible crowd. The air around you right now is pressing on your body, but evenly enough that you do not feel it as a particular touch, unless it moves, changes temperature, or carries moisture. The difference between air, water, and stone is not that one is real matter, and the others are less real. It is how densely their particles are arranged, how strongly they interact, and how freely they move. Matter can be gas, liquid, solid, gel, foam, crystal, fibre, and more. Each state gives touch a different grammar. Foam is especially interesting because it feels soft, partly because of emptiness. A foam cushion contains a network of solid material, and many pockets of gas. When you press it, the gas pockets compress or shift and the solid walls bend. The material gives way easily at first, then resists more as the structure collapses and densifies. A sponge works similarly. Its softness does not come from the atoms themselves being vague. It comes from a large-scale structure full of spaces that can change shape. This is a good reminder that empty space is not opposed to solidity. It can be part of how solidity behaves. A sponge is mostly space, but it has a structure that lets it hold water, compress, and spring back. Atoms are mostly space too, though in a much deeper and more quantum sense. In both cases, structure matters more than simple fullness. A feather feels light and delicate because its structure is thin, flexible and spread out. It bends under tiny forces. It touches the skin over a very small pressure range, often moving with the air before it presses much at all. A brick feels heavy and hard because its mass is greater and its structure resists deformation, but both are matter. Both are built from atoms. Both rely on electromagnetic interaction to keep their shape. The difference is arrangement at many scales. The feather's softness begins not only in molecules, but in the branching architecture of barbs and tiny structures evolved for flight and insulation. The brick's firmness begins in mineral particles fused and hardened into a dense form. Touch reads architecture. It does not just read substance. This is why two objects made from the same basic material can feel different. A sheet of paper, a block of wood, and a pile of sawdust may all come from plant matter, but they respond differently. Paper bends and crinkles because fibres are pressed into thin sheets. Wood is stiff because its cellular structure and grain support force in particular directions. Sawdust flows like a granular material because the pieces are separate and can rearrange. Grain matters, shape matters, size matters, connection matters. The atomic ingredients are only the beginning. The structure built from them is what your hand encounters. Granular materials like sand are wonderful because they sit between solid and fluid behavior. A single grain of sand is solid and hard. A pile of sand can be poured. Step on dry sand and it shifts under your foot. Pack it with water and it holds shape well enough for a sandcastle, at least until the tide arrives, with its usual lack of respect for architecture. Sand feels grainy because your skin detects individual particles and their movement. It can support weight because grains press against one another and lock into temporary arrangements. It can flow because those arrangements can break and rearrange. The same material can seem solid or fluid depending on how it is confined, how much pressure is applied, and how the grains interact. Powders behave similarly. Flour, sugar, salt, dust, and soil are all collections of small particles. They can pile, flow, clump, stick, or compact. Their touch depends on grain size, moisture, shape, and surface forces. Fine flour can feel soft because the particles are small and distribute pressure gently, but it can also pack and resist. Salt feels sharper because of crystal shape and size. Dust sticks because tiny particles have high surface area and can cling through weak forces, moisture, and static effects. The sensation of powder is not the sensation of a continuous solid. It is the skin reading countless small contacts, each one still governed by the same invisible repulsions. At the other end, polished glass feels smooth because its surface has very small irregularities compared with many other materials, and because it can present a continuous hard surface to the skin. But glass can also feel cool because it transfers heat from your skin more efficiently than fabric or wood. Metal often feels cooler still for the same reason, especially if it conducts heat quickly. This is why a metal chair in a cold room seems colder than a wooden one at the same temperature. Your skin is not measuring temperature alone, it is sensing heat flow. The material that steals warmth faster feels colder. So even coolness, which seems like a simple property, depends on an interaction between your body and the object. This is also why texture and temperature are difficult to separate in experience. A smooth cold surface can feel harder than a warm one. A warm blanket feels softer than a cold damp cloth, even if the mechanical pressure is similar. Wetness changes friction and heat transfer. Oil changes how surfaces slide. Soap reduces friction in one setting and creates slippery resistance in another. The brain combines all of these signals into a single impression. Touch is not a list of separate data points. It is a blended perception, like a stew of pressure, vibration, temperature, movement, and expectation. Sometimes a stew with too much information, as when you reach into a sink and touch a mysterious wet object you are not emotionally prepared to identify. The illusion of solidity is not that solidity is fake. It is that solidity is not what common sense first imagines. We imagine the world as filled with hard stuff, packed tightly from surface to centre. We imagine contact as direct meeting. But matter is not built like that. It is made of atoms, mostly spaced by volume, structured by fields and quantum rules. The hard stone is not hard because it is solid all the way down in the everyday sense. It is hard because its particles are arranged in a way that resists rearrangement. The soft skin is not soft because its atoms touch differently. It is soft because its tissues deform more easily. The pillow is not less real because it yields. The stone is not more real because it refuses. Both are different expressions of the same underlying physics. This can be surprisingly difficult to feel, because our senses are scaled for the world of objects, not atoms. The brain gives us a practical world of surfaces. It does not show us electron clouds. It does not report quantum states. It says stone, skin, fabric, water, floor. It says firm enough to stand on, too hot to hold, soft enough to sleep on, sharp enough to avoid. This is exactly what a body needs. A creature that paused to contemplate the atomic emptiness of a falling rock would not necessarily be better prepared than one that simply moved out of the way. Our senses simplify reality in the service of action. They give us the version of matter we need to live. But sometimes, in calm moments, we can hold both views at once. The stone in your hand is solid. It has weight, texture, temperature, and shape. It also consists of atoms whose volume is mostly structured space. Its hardness is a collective behaviour. Its surface is a region of force. Your skin is soft and sensitive. It also consists of molecules made of atoms, held apart and together by invisible interactions. When the two meet, there is no simple final contact, but there is a real exchange of force and information. The stone presses into skin, skin deforms, nerves speak. The brain says hard, cool, rough, heavy. The experience is real, but it is an interpretation of a deeper event. This layered view helps explain why touch can be both reliable and deceptive. Reliable, because the physical world responds consistently. A sharp edge will usually feel sharp. A soft cushion will usually feel soft. A hot pan will usually make its point quickly and without subtlety. Deceptive, because the feeling does not reveal the underlying mechanism directly. A table feels completely filled, even though atomic structure is mostly space. Metal feels colder than wood at the same temperature because of heat transfer, not because it contains more coldness. A heavy small object can feel heavier than expected because the brain compares weight with size. A surface can feel wet because it is cold and slippery, even if no water is present. Touch is useful, but it is not a transparent window into physics. It is a skilled interpreter, and interpreters sometimes choose practical meaning over technical detail. The brain's interpretation of solidity also depends on movement. If you simply rest your hand on a surface, you feel pressure. If you push, you feel resistance. If you tap, you feel impact and vibration. If you scrape, you feel texture. If you squeeze, you judge softness. If you lift, you judge weight. Each action asks the material a different question. The world answers through force. A stone answers, I will not deform much. A sponge answers, I will deform readily. A rubber ball answers, I will deform and return. Clay answers, I will deform and remain changed. Water answers, I will move aside but not instantly. Air answers, mostly yes, unless I am moving very fast. Touch is a conversation, and your movement supplies the grammar. Solidity also emerges from boundaries. Your body needs to know what is you and what is not you. Skin provides one boundary, but the brain can extend that boundary through tools and clothing. After wearing shoes for a while, you do not feel the full pressure of them constantly unless something changes. Your brain treats them almost as part of the normal body environment. A skilled driver can feel the road through a car. A musician can feel the instrument as an extension of the hand. A surgeon can feel tissue through a tool. In each case, the solidity of the world is sensed through chains of material interaction. Repulsion and vibration pass from object to tool, to hand to nerves to brain. The boundary of touch can move outward, even though the receptors remain in the body. This makes the solid world partly a relationship between organism and environment. A rock may be solid whether or not anyone touches it, in the sense that its structure resists deformation. But hardness as a feeling requires a body. Smoothness as a feeling requires skin or some sensing system. Temperature as comfort or discomfort requires a living range. The material has properties, and the body has ways of detecting them. The experience arises between them. Solidity is objective in its physical resistance, but subjective in its felt quality. A mattress that feels soft to one body may feel firm to another. A floor that feels warm to bare feet may feel cold after a hot bath. The same world can answer differently depending on who is asking and how. Even animals live in different touch worlds. A cat's whiskers detect delicate changes in air and nearby surfaces. A mole reads underground tunnels through sensitive skin and hairs. An octopus explores with arms covered in sensory structures, tasting and touching in ways difficult for us to imagine. Insects feel the world through legs, antennae, and tiny hairs. Different bodies translate matter differently. The underlying atoms and forces are shared, but perception is shaped by anatomy. Human touch is not the universal form of touch. It is our version, tuned to hands, skin, tools, warmth, social contact, and the practical business of moving through a world of medium-sized objects while trying not to trip over the furniture. The illusion of solidity is therefore also an illusion of scale. At the atomic scale, matter is spacious and ruled by fields. At the human scale, those fields combine into surfaces. At the biological scale, surfaces become sensations. At the emotional scale, sensations become comfort, danger, care, irritation, memory. A wool blanket may be slightly scratchy because of fibre structure, but it may also feel nostalgic because of childhood winters. A stone may be physically hard but emotionally soothing if warmed by the sun and held in the hand. Physics begins the sensation, but the mind completes it. Still, the physics remains quietly underneath. Soft skin and hard stone do not truly touch as little solid things. They approach until electromagnetic and quantum resistance create a boundary. The stone barely yields. The skin yields more. Pressure spreads through tissue. Receptors respond. The brain builds the experience. If the stone is rough, tiny peaks create changing pressure. If it is smooth, the pressure is more even. If it is cold, heat leaves the skin. If it is warm from sunlight, energy flows the other way. A single object can feel many ways depending on its surface, temperature, motion, and the state of your own body. Solidity is not a simple yes or no. It is a richly detailed answer to contact. This is why everyday objects deserve a little more wonder than they usually receive. A wooden spoon is not just a utensil. It is a structured material that feels warm compared with metal because it transfers heat differently, light because of its density, slightly textured because of its grain, firm because of its cellular structure, and comfortable because its surface and shape spread pressure across the hand. A ceramic mug feels smooth, hard and warm when filled with tea because its material resists deformation. Its glaze presents a polished surface and heat moves through it into your skin. A blanket feels soft because its fibres bend and trap air, because pressure is distributed gently, because warmth is held close. These are not separate miracles. They are the everyday outcome of atoms arranged well. And your own body is one of those arrangements. Soft skin covers firmer structures, fat cushions, muscle contracts and yields, bone supports, cartilage reduces friction, tendons transmit force, blood carries heat, nerves interpret. You are not a single kind of solid, but a living assembly of materials, each with different mechanical properties, all working together. Your body can be soft to the touch and strong in motion. It can sense a feather and lift a heavy object. It can be warmed, cooled, bruised, comforted, startled, soothed. The physics of touch is not outside you. It is part of how you are built. So when we call solidity an illusion, we should be careful. It is not a lie. It is a simplified truth at human scale. The floor really supports you. The stone really resists your hand. The pillow really yields. But the explanation is not that these things are solid, in the naive sense of being filled completely with hard substance. They are solid because enormous numbers of atoms maintain patterns of resistance. They feel the way they do because your body is able to detect how those patterns respond. The illusion is only in the picture, not in the experience. Perhaps that is why the idea is not cold or empty, even though it tells us that nothing truly meets in the way we first imagined. The world is not less intimate because contact is mediated by forces. It is intimate because those forces are precise enough to become feeling. The softness of skin, the hardness of stone, the warmth of a mug, the weight of a blanket, the smoothness of glass, the roughness of bark, all are ways the universe becomes available to a body. The fact that it happens through invisible interactions does not make it distant. It makes the closeness more remarkable. Right now, whatever is supporting you is performing one of these material answers. If it is a bed, it is yielding and holding. If it is a chair, it is distributing pressure through fabric, foam, wood, metal or plastic. If your hands are folded, skin is pressing into skin, each side soft, warm, and quietly resistant. If your feet are on the floor is pushing back with the calm authority of arranged matter. Every sensation is a reminder that solidity is not a simple substance, but a behavior. Matter is always answering the question of nearness. And as that thought settles, the final turn of the journey comes into view. If nothing truly touches, and yet everything we feel depends on these near meetings, then the world is not a place of direct contact but of relationships. Bodies, objects, surfaces, air, warmth, pressure and memory all held together by interactions. The strange comfort is that the world does not need to truly merge with us in order to reach us. It only needs to come close enough for forces to speak and for the skin to listen. By now, the simple act of touch has become a little less simple, but perhaps not less familiar. Your hand is still your hand. The surface beneath you is still there. The blanket still feels like a blanket. The chair still holds you. The floor still waits below with its usual patience. Nothing has floated away just because we looked at it more closely. And yet the picture underneath has changed. What first seemed like direct contact has turned out to be a layered process, built from atoms that are mostly space, electrons that repel, quantum rules that preserve structure, skin that deforms, nerves that signal, and a brain that turns all of that into the feeling of the world. It would be easy to hear the phrase "nothing truly touches" and think it means we are somehow separated from everything. A person might imagine each object surrounded by a tiny invisible loneliness, every surface held just beyond every other surface, the whole universe almost meeting but never quite managing it. That sounds a bit bleak at first, like a cosmic waiting room where every chair is close but none of them are available. But the more carefully we look, the less lonely the idea becomes. Because what matters in touch is not merging. What matters is interaction. The world reaches you not by becoming you, but by influencing you. It presses, warms, cools, vibrates, supports, resists, and responds. That is enough to build every sensation you have ever called contact. In fact, it may be better that things do not truly touch in the simple sense. If the atoms in your hand and the atoms in a table could simply occupy the same place, there would be no firm boundary, no stable surface, no useful resistance. The table would not be a table in the way you need it to be. A chair could not hold you. A cup could not contain tea. Your skin could not protect your body. The world would lose the separations that make form possible. Touch depends on closeness, but it also depends on difference. You can feel a surface because it is near you and because it remains other than you. It does not disappear into your hand does not disappear into it. Between them is not emptiness in the ordinary sense, but a structured refusal, a tiny region where forces become strong enough for matter to answer matter. That answer is everywhere in your life. You wake because a mattress supports your body and light touches your eyelids without becoming part of them. You stand because the floor pushes back through the soles of your feet. You dress because fabric can rest against skin without merging with it. You wash because water molecules interact with oils, salts, and surfaces. You eat because teeth, tongue, and food meet through pressure, texture, heat, and chemistry. You carry objects because your fingers can grip them, not by fusing to them, but by friction, shape, and carefully controlled force. You move through the day inside a web of almost contacts, and that web is so reliable that it becomes ordinary. The miracle is not that physics is strange. The miracle is that its strangeness becomes breakfast. Consider the floor beneath you. It may be wood, stone, carpet, concrete, tile, or something softer. At your scale, it is a surface. At the atomic scale, it is a vast arrangement of particles and fields. It is not perfectly still, not truly solid in the naive way, not filled edge to edge with hard substance. Its atoms vibrate, its molecules hold patterns, its electrons occupy allowed states, its structure resists compression. And because of that resistance, your body does not fall through. The floor is not doing anything dramatic, it is not thinking about support, it is not straining heroically beneath you. It is simply being matter according to the rules of matter. Yet the result for you is safety. You can stand, walk, sit, rest. The deepest physics becomes trust. This is one of the quiet comforts of the physical world. It does not need to be simple in order to be dependable. A door is complicated at the atomic level, but it still opens when you turn the handle. A blanket is an enormous structure of fibers, molecules, air pockets, heat transfer, friction, and pressure, but it still feels warm across your shoulders. A wooden table contains a history of sunlight, growth, cells, water, chemistry, cutting, drying, shaping, and polishing, but it still holds a cup. The universe does not require you to understand all of its layers before it lets you lean on them. It allows you to live first and wonder later. That may be why this question feels so satisfying. What is touching you right now is not just a scientific puzzle. It is an invitation to notice the hidden effortlessness of being supported. You may be sitting in a chair, but the chair is also a material structure distributing your weight. You may be lying in bed, but the bed is also a system of fibers, foam, springs, fabric, air, and molecular forces adjusting around your body. Your clothes may feel still, but they are in constant small contact with your skin, shifting as you breathe, warming as they trap air, pressing lightly where gravity and posture bring them close. The air may seem absent, but it is pressing against you from every side, carrying heat away, delivering oxygen, brushing the skin when it moves. You're never really untouched. You're surrounded by interaction, and yet you are not dissolved into it. That is the balance. The world reaches you without consuming you. The boundary of your body remains. Your skin holds you together. Your nerves tell you what is near. Your brain decides what matters. The same forces that prevent objects from passing through each other also allow the body to keep its shape. The same quantum rule that helps matter resist overlap helps atoms form the stable structures of living tissue. The same electromagnetic interaction that makes a table push back also allows nerve cells to send signals. Touch is not a break in the boundary between you and the world. It is the boundary doing its work. This makes contact feel less like a collision and more like a conversation. A hard surface says it will not move much. A soft surface says it will move for a while and then hold. Warm metal says it can pass energy quickly. Wool says it will catch on the skin in tiny ways. Glass says it is smooth and cool. Water says it will move aside while still pressing everywhere it can. A pet resting beside you says, through warmth and weight and slow movement, that another living body is near. These are not words, of course. No pillow has ever offered a formal statement on its mechanical properties, though some old pillows have certainly made their opinions known. But touch is a form of information. Matter speaks through resistance, and the body listens. The comfort lies partly in how much of this listening happens without effort. Your skin is monitoring pressure right now. Your muscles are adjusting posture. Your brain is quieting constant signals that do not need attention. You're not required to consciously manage every point where your clothing meets your body or every place your weight meets the chair. If you had to think about all of it, the day would be impossible. Instead, the nervous system edits the world into usefulness. It tells you only what changes, what matters, what may harm you, what may comfort you. The rest becomes background. The chair disappears until you shift. The blanket disappears until it slips. The pillow disappears until it becomes too warm, too flat, or mysteriously located nowhere near where pillows are meant to be. There is something generous about that filtering. The body protects you from the full noise of contact. It gives you a quiet version of reality, not because reality is quiet, but because you need quiet to live. Underneath every still moment is activity. Atoms vibrate, molecules jostle, air moves, heat flows, signals rise and fade, forces balance, your brain receives, compares, predicts, and ignores. A peaceful room is not physically empty of events. It is full of events that have settled into balance. Rest is not the absence of physics. Rest is physics behaving steadily enough that the mind can stop paying attention. This is also why touch can be calming. A steady pressure can tell the nervous system that the body is supported. A blanket can feel soothing because it spreads gentle force across the skin. A hand held softly can signal safety, connection, and presence. A warm cup can bring comfort because warmth, weight, and shape combine into a familiar pattern. None of this requires true contact in the tiny solid object sense. It requires reliable interaction. It requires the world to push back in ways the body can understand. Closeness is not measured only by whether atoms meet. It is measured by whether forces carry meaning. When you think of it this way, the fact that nothing truly touches does not make a hug less real. It makes a hug more interesting. Two bodies come close, skin deforms, warmth transfers, pressure spreads, breathing changes, heart rates may settle. The brain interprets the pattern as comfort, affection, reassurance, or recognition. At the atomic level, electrons still resist overlap. The bodies remain distinct. That distinction is necessary. A hug is not becoming one object. It is two separate bodies close enough for each to affect the other. The separation is not a failure of intimacy. It is the condition that allows intimacy to happen at all. The same is true of holding a hand. You feel warmth, pressure, texture, movement. The other person's hand is not physically merging with yours, and that is precisely why you can feel its shape. The boundary lets sensation exist. If everything blended into everything else, touch would not become richer. It would vanish. The world must keep some distance in order to be felt. That tiny distance, maintained by forces too small to see and rules too strange to picture, is the space where experience appears. This may also soften the way we think about separateness more generally. Physics does not show us a universe of isolated things that never affect one another. It shows us a universe where every object is defined through relationships. Atoms are not stable alone in some simple, hard sense. They are systems of interactions. Molecules are relationships among atoms. Solids are relationships repeated into structure. Bodies are relationships among cells, fluids, tissues, and signals. Touch is a relationship between matter and nervous system. Even identity at the physical level is maintained through boundaries that interact. You're separate from the chair, but not disconnected from it. You're separate from the air, but breathing it. You're separate from the earth, but held by it. You're separate from the world, but continuously informed by it. There is a practical humility in this. Our senses tell the truth at the level they are meant to serve, but not the whole truth. A surface feels solid, and that is true enough to set a cup on it. A wall feels impenetrable, and that is true enough to avoid walking into it. A blanket feels soft, and that is true enough to sleep beneath it. But beneath these useful truths are deeper truths. Solidity is organized resistance. Contact is force translated into sensation. Emptiness can have structure. Boundaries are not simple lines, but regions where interactions become important. The world is not less real because our first picture of it was incomplete. It is more real than that picture could hold. This is often what science does at its best. It does not always destroy the ordinary, more often it deepens it. The stars remain stars after astronomy. A flower remains a flower after biology. A cup of tea remains a cup of tea after thermodynamics, although perhaps slightly cooler if the explanation goes on too long. Touch remains touch after atomic physics. The difference is that now the simple sensation carries a hidden depth. The surface beneath your hand is no longer merely a surface. It is an emergent boundary made from fields, particles, and perception. The softness of fabric is no longer merely softness. It is the large-scale behavior of fibers, air, heat, friction, and skin. The support of the floor is no longer merely support. It is matter obeying rules so consistently that your body can trust them without thought. As we come back to the question we began with, what is actually touching you right now? The answer is both ordinary and strange. The chair is touching you, in the practical human sense. The bed is touching you. The blanket, the air, the clothing, the floor, perhaps the device you are listening on, all are touching you in the language of daily life. But beneath that, what is touching you is force, electromagnetic interaction, quantum order, material structure, pressure moving through skin, signals moving through nerves, a brain building the feeling of contact from patterns it has learned to trust. You're being touched by a translation of the physical world. That translation is not a mistake. It is one of the great achievements of living bodies. A plant bends toward light without seeing as we see. A bacterium responds to chemicals without smelling as we smell. An animal feels vibration through the ground or water. A human fingertip can read a surface, recognize an object, and know comfort from danger. Life turns interaction into information. Your sense of touch is one way the universe has become aware of its own boundaries. That may sound large, but it begins with something small. A fingertip on cloth, a shoulder against a pillow, feet resting on the floor. Notice one of those points now, gently. Not all of them, just one. The place where your body is most clearly supported. There is pressure there, perhaps warmth, perhaps a little stiffness or softness. The feeling may become clearer as your attention rests on it. What you're noticing is not atoms colliding like tiny marbles. It is the end result of many levels of reality cooperating. The material beneath you resists. Your skin changes shape. Receptors respond. Your brain allows the sensation into awareness. For a moment, the background becomes foreground. The ordinary becomes detailed. Then, if you let it, it can fade back again, doing its work without needing to be watched. That fading is part of rest. The world continues to hold you even when you stop thinking about it. The chair does not require attention to support you. The floor does not need praise for remaining beneath the room. The blanket does not ask you to understand textile physics before it keeps you warm. Matter simply behaves. Your body simply receives. And somewhere in that simple exchange, sleep can begin to find its way in. So perhaps the comfort is not that the world truly touches us, but that it does not have to. It can remain itself and still reach us. It can keep its boundaries and still support us. It can be mostly empty at the atomic scale and still feel full at the human scale. It can be governed by strange quantum rules and still produce the plain softness of a pillow. It can never quite meet in the old imagined way, and yet give us every hug, every footstep, every warm mug, every smooth stone, every hand held in the dark. And if tonight this thought has made the world feel a little less solid, let it also make it feel a little more patient. Beneath every surface is a balanced refusal. Beneath every pressure is an interaction. Beneath every feeling of contact is a long chain of matter and mind working together. You're not floating apart from reality. You're resting inside its relationships. As your body settles, you might let the question return one last time. What is touching you right now? Maybe it's a blanket, a mattress, a chair, a sleeve, the air, the quiet weight of your own hands. Whatever it is not reaching you by becoming you. It is reaching you by coming close enough for the hidden forces of matter to speak. And your body, old and wise in ways no textbook needs to teach it, knows how to listen. If this gentle journey through the physics of touch has brought you a little calm, a little curiosity, or simply a softer way to notice the room around you, I would be grateful if you liked the video and subscribed. It helps this quiet space of science find others who may need a peaceful place to land. And if you feel like leaving a thought behind, tell me where you're listening from and what is touching you in this moment. A pillow, a blanket, a cup, the floor, the evening air. It is a small answer to a very deep question, because in the end, the world that never quite meets is still the world that holds us. Not through direct merging, not through tiny solid edges finally colliding, but through forces, structure, warmth, pressure, and the steady intelligence of the body. The universe keeps its smallest distances, and somehow from those distances it gives us closeness. Sleep well, fellow traveller, wherever you are, and whatever gentle surface is holding you tonight.